everything up that I need to get up. YouTube's live. Okay, cool. Well, welcome in everyone. Slim, aka Academy of Useless Ideas. Thank you so much for the raid. I hope the rest of your stream was good. I was kind of lurking after we talked about the question, but I do really appreciate hearing your thoughts on that linear algebra type problem. Anju, hey, welcome in. I think you're in the YouTube chat the other day, right? Welcome over to the Twitch side if so. And regardless, welcome in. Hey, Desson. Due to my accent, sometimes when people do math, some of them look at me in horror and ask if I said meth. Reading your name, I started a parody account called Donda's Meth, in which things would be more erratic. That would be hilarious. She's a DayZ streamer, but I typed in her chat and she did this really like that's a pretty common joke about my name, Donda's Meth, and Fish, who's a cool person, that made like a funny little like joke about it. So yeah, that clip like makes me laugh. And hey, $10. You work in a meth lab? Yeah, that game like Schedule 1 where you get to like make and sell meth. That seems like a funny game to like lean into that bit with. Yeah, this is the reading group. So for the next 2 hours, we're going to be talking about general relativity out of this book here. And we're not really on the real general relativity yet, but we're starting on chapter 3, which goes over Newtonian physics. But there's quite a few new things in this that I didn't learn in my Newtonian physics class. The differential geometry, yes. We've already covered a little bit of it in chapter 2. It was towards the end. Thanks for hopping in the call, Felix. I'll get in there in just a second. Oh my god. So yeah, this is where they get like a little bit into differential geometry. They start out just with spheres because those are the easier things. They talk about like the general kind of axis symmetric geometry. And they do an example for peanut. Yeah, and so in chapter 3, the interesting kind of math stuff. I was like, chapter 8 is just on geodesics, yeah. I assume we're about to talk about with Femvox here, but we talked about functionals here, which are new for me. So that's the interesting kind of like math thing that I think are just studied like squarely in math as well, and not just a physics thing. Thanks for the follow, Anju. But I don't want to get too far ahead of myself because this is the stuff we're going to discuss right now. So let me hop in the call with Fembox here. Hey, Fembox. You're still on mute. Ooh.
Sorry, I was muted there.
I gotcha now. How's it going?
Doing good, doing good. I had you on 2 different voice channels there, so I just fixed it.
Oh yeah, that's always disorienting. I had the same problem with like Zach's classes too.
Yeah, doing good. How are you?
I'm doing pretty good. Thanks for asking. So, were you able to get through chapter 3 for the reading?
Yeah, I finished it up. I only read the last couple sections this morning, but yeah, I read it.
Okay, nice. I only read the last like little bit like yesterday, I think. Inertial frames refer to math frames, or I never heard of a math frame. As far as I know, it's just a physics frame. They inertial frames are a certain type of frame. Uh, they're a little bit more restricted than a kind of general frame. Um, I think an initial frame is just a frame where you're not allowed to be rotating, but it can do other things. Like it can have a constant tilt. It can be translating, and it can have an offset. Like these are the different ways that inertial frames can be different from each other and no other ways.
You know, Don, I think it was Fizzbuzz was telling me last week, and I might have this wrong, so take it with a grain of salt. But I think he was telling me that you can think of inertial frames and as having like a group structure some way, in some way.
Oh,
Isn't that neat?
yeah. I'd be interested to learn more about that. That's not saying that looks like the
Yeah,
math
me
frame.
too. Me too. I think they said it's called like the Galilean group.
Oh, I think I've heard him talk about that then. I feel like Galilean like frames or transforms or something are definitely a thing. And I wonder if maybe the group is or it makes sense there's a Galilean group, I guess.
What does
Um,
TM stand for? Maybe tensors? Oh, here's Dr. Cook. Hey, Dr. Cook.
it's TM, so it's a VS, so a group.
A vector space, I guess.
Oh, okay, yeah. Maybe like translational motion or no? There's no way that's what TM is. Yeah, I never heard of a math frame, but I guess those have a meaning somewhere. Okay. Let's see. There were a few things in this chapter that were a bit weird.
Yeah.
The first thing that weirded me out is figure 3.6. I had to really stare at this thing to make sense of it because I was confused by the direction of things relative to equation 3.5. I forget what I guess my question was. So I should have thought about this before the group again to remember why I was confused by it, but it was something about
Uh,
the sign of being x minus vt in the direction of this arrow pointing towards x prime. I think it ends up making sense, but I had to really think about it.
I think it makes sense.
Because a
So it
coordinate
makes
in
sense for
x
t
prime,
equals 0.
it's a coordinate in x minus something. Yeah, I think it makes sense.
Yeah.
It definitely feels weird though. Like I with the minus vt, I would have expected the arrow to point the other way, but I think it is properly that way.
Yeah, because you want to think of a point, right? Imagine there was a point written over. Imagine there was a point in there, maybe to the right of both of the y-axes, and call it point P. And then point the x-coordinate of point P and the y prime and the primed frame is going to be smaller than the x-coordinate of point P in the unprimed frame.
Yeah.
Oh, isn't that
Um,
right? I think that's right. Or more negative, I should say, maybe.
or yeah, or maybe it was something about like the 0 point. Or like when t equals 0, the frames are right on top of each other.
Yeah.
But it seems like the moment in time where this is being shown, I guess it will be a positive time. I was for reason I was thinking it might have to be a negative time, but I think it is a positive. And I guess you're allowed to have a negative time depending on how you're counting things. Hey Storm, this is the general relativity reading group. So we're just talking about chapter 3 of this textbook, and then we're going to get into solving some problems. Dr. Cook, it's on mobile now, but walk home soon to be on laptop. You can only stay for an hour today. Okay. And then Fizzbuzz said he probably wouldn't be able to make it at all, unfortunately.
I know, we're in trouble.
Yeah.
We're in trouble.
Okay, scrolling down. UCLA for actual education? Yeah. I think I was mostly okay with this stuff until the end of the chapter, is where things got sketchy. Oh, it was cool to see that there's a gravitational potential in the same way there's an electric potential. You know, the formulas are nearly the same.
Yeah.
Um,
Yeah, section 3.3 was where I was afraid my grad, div, and curl were going to start letting me down again.
I just put it all in terms of this of how we learned it, or like even that chart where they compare it to E and M stuff made it really. I thought it made it a lot easier to understand what these equations mean.
Yeah.
So it's kind of convenient that we did the E and M before this. Because it probably would have been lost.
Well, I was still lost, but I think the E&M helped.
Okay, fair enough. Oh, this whole thing, I was completely lost with the what the point was of making a distinction between inertial mass
Yeah, me too.
and
Yeah, me
gravitational
too.
mass.
I was gonna say that if you didn't. I was like, well, inertial mass and gravitational mass, and then they belabored the point, and then they said, well, and it turns out that they're equal anyway. So maybe that's going to come back later, and we're going to have more understanding of why there's a distinction.
Yeah, I'm like mass is more or less just a count of the atoms. Like you could, if you know what molecules make up that mass, you can literally get the count of atoms and how would that possibly be different for inertia versus gravity. But I don't know. Yeah, maybe you're right. It will, maybe it'll come back up. That is asking if I've heard a book called Irodov. No, I haven't. Um, and then 3.5. Or did you have anything? I assume 3.5 is gonna be like the big like sticking point. Do you have anything on chapter 3 before 3.5?
Uh, I mean, not really. I thought most of it made sense.
Okay.
Like I said, like section 3.3, I felt like I was weak with the idea of a potential versus a field, and they were talking about Gauss's law again, and I was like, okay, I remember that, but
Mm-hmm.
oh,
Hey,
hey,
SG1.
Cook just got on.
Oh, okay. You're on mute if you're trying to talk. Oh, you're off mute now.
Hey, am I audible?
Yep, we gotcha.
Sure are.
Hey, okay, sorry to crash the party.
No, please do.
I'm walking out, so there might be some wind, but I heard a discussion of inertial versus gravitational mass, and I couldn't help myself.
Yes. Why?
Okay,
Yeah. Why would we care about this?
okay, it's a really huge point. It's something you should have cared about when you first learned Newtonian mechanics if you were really pedantic, because mass inertially is your resistance to acceleration, right? You push two objects with the same force, one accelerates more. That's the less massive object by definition of what inertial mass is. Inertia being the term referring to resistance to changes in velocity. And now the problem is, why is that the same? Why should that at all be the same quantity that determines your gravitational attraction to another object? Like in principle, that could be something completely different. So it should have
Hmm.
felt like a big mystery in Newtonian mechanics, and it is in Newtonian gravity, why those two masses are the same. The mass that gravitationally attracts other masses and the mass that has resistance to changes in velocity. Because the latter, inertial mass, I mean, you could imagine measuring that with totally non-gravitational forces.
Hmm.
And so this is
Huh.
actually this is Einstein's most beautiful idea. This is the equivalence principle. So imagine like there's a lot of different ways to say this, but like okay. Imagine we're well hmm. Like imagine we're like in a actually I'll just use Einstein's example. So imagine we're in a big chest, like treasure chest in outer space, and like there's a rope tied to the top of it. And initially we're just floating freely in the chest. There's no gravitational forces, so it's like the astronauts, you know. You push off the wall and you just move in a straight line at constant velocity, Newton's first law. But now imagine some great hand of God grabs the rope attached to the top of the chest and starts pulling it at a constant acceleration relative to what it was initially. Then you would have this apparent gravitational field, and every object in that box would accelerate downward with the same acceleration, i.e. the acceleration which with the external hand is pulling the chest. And so what Einstein's noticing is that these two phenomena are the same, where if you're in a non-inertial reference frame that's moving at constant acceleration with reference to an inertial reference frame, all these masses, they appear to have this fictitious force that's proportional to their inertial mass. And that's because they're trying to stay in the original inertial frame. And so this is the idea that led Einstein to realize that gravity is a fictitious force that arises due to us being in a non-inertial reference frame. And that this is one of the big pieces of evidence that the gravitational mass is equivalent to inertial mass. It's called the equivalence principle.
Oh yeah, physics and depression mentioned that last night. I was at his stream and he was talking about that.
Oh yeah, I saw
It doesn't come.
something
It
like that.
comes up in this book in chapter 6, I think. I just looked ahead.
Or like, have you been in those like fair rides where you get in and it spins around, and you start
Yeah,
to stick to the wall and
Oh
they
yeah.
drop the floor out, but you don't fall?
yeah.
Mhm.
So in that frame, if you were in that frame doing the laboratory or whatever, you could have like a 1 kilogram peanut, and it would appear to have like 1 kilogram times the centrifugal acceleration outward. A 2 kilogram peanut would have a 2 kilogram times the same centrifugal acceleration, because that apparent force that you're witnessing is arising not from some like fundamental interaction, like something pushing on something. It's a gravitational force. There is no gravitational force. You're just seeing this apparent acceleration because you're in a non-inertial frame.
Hmm.
And,
Yeah, like or
yeah.
like they say, if they could set up a space station in outer space, if they could rotate it around the center, then you'd have a sort of an imaginary gravity holding you to the outside wall or something.
Yeah, and then
Yeah.
if you didn't know it was spinning, you would measure this force where every object would have the force proportional to its inertial mass, and you would wonder, why is this like outward directed force proportional to the inertial mass of every object? You would wonder that if you didn't know. That is because of this non-inertial spinning reference frame. And so when you're standing on the Earth and you feel this gravitational attraction pulling you down, it's really because you're accelerating upwards. Yeah, sorry, that was a rant. Okay. I haven't sidetracked this too much, have I?
No,
No.
that's that thing that we were just talking about. So, thank you for that.
Yeah, so I haven't looked at chapter 3 in a while. Is that the main thing? Chapter 3?
No.
Or
uh, the next section is talking about Lagrangians and then like action.
oh, okay.
And so I think that's gonna be
I
the
must be
main weird
home.
thing. Okay.
Okay, I'll hop on the laptop in like 5-10 minutes. See you in a bit.
See you in a bit.
Okay.
Okay. Well, that at least answers the question why we should care about inertial and gravitational mass, or not assume that they're just the
Well,
same thing.
yeah. Yeah, he did say in the book, this equality between a number mi, which controls inertia in the general dynamical law for all forces, and a number mg that measures the coupling strength to a particular force, gravity, is truly remarkable. And when I read that, I thought, okay, I better pay attention then. I didn't understand why it was remarkable.
Yeah, I was like, I'll take your word for that, but
Yeah. Because I was thinking about it, like you do physics and just as sort of an introductory physics and you learn about the mass of an object. And how do you find out, like if they give you like a 2 kilogram mass, how do we know it's 2 kilograms? Well, because we put it on a scale, right? We let the earth suck on it and we see what the spring on the scale says. It says 2 kilograms. So it felt like that mass that we determined for these objects we're using, and when we slide it up a slope or something and we want to know how much force we have to put on it. It didn't seem strange to me that it would be the same mass in the F equals ma versus the g m1 m2 over r squared, setups. But I guess I understand a little more now.
yeah, and I guess you could try to measure mass without gravity by either pushing on it and measuring the
Yeah.
acceleration, or like
Yeah.
spinning it around or something.
Yeah, that's right. Yeah, like Dr. Cook said, you don't really have to use a spring scale.
Yeah.
You don't have to use gravity. I mean, you could measure it a different way, I guess.
And hey, Naman, I do study math too. This is a thing this is a thing that I do on Saturdays. These like reading groups on general relativity, because I think it's really cool. Okay.
So what did you think about the Euler-Lagrange equation?
I mean, this is the first time that I've seen any of this, so it feels very strange. Like, for first off, just defining L equal to kinetic energy minus potential energy, it just feels very random. It does seem to lead to very clean forms, which I guess is why they do that. I did see the thing, or I was looking when you asked this impression about this equation, and I do think it was helpful to see like that the Euler-Lagrange equation is fancy F equals ma.
Yeah. He was talking about that for a while.
Yeah, and I feel like I should just be able to look at it and remember which one is F and which one is ma, but now it's kind of I can't immediately remember which one is which.
The force is partial dl, partial dx.
This is partial dl. Okay.
That's the one that looks kind of like a force.
Right, yeah, because kinetic energy doesn't, or dk dx is 0 because kinetic energy doesn't depend on position. And so this is basically dv dx, and that's just a force. Okay, yeah. That trick that he did with like noticing that certain things, like the kinetic energy that goes to 0 if you derive it with x, and the potential energy going to 0 if you derive it.
I'm gonna say differentiate.
Differentiate. Yeah. Okay. I forgot. Yeah. But like noticing those two things that differentiate to 0, so you can add them into the equation for free, it was kind of neat.
Yeah. Yeah, that was good. Like I said on his, like I chatted in his stream, it was ChatGPT that first told me that.
Yeah.
I thought, man, I've watched a bunch of videos on Euler-Lagrange. I've read like 2 different books on it, and I feel like nobody had pointed out the relationship of one of the terms kind of looking like a force and the other one kind of looking like a time rate of change of a momentum.
Yeah.
I was like, ChatGPT tells me this. What the hell?
when it comes down to this action functional thing, so I've never seen a functional before either. And I immediately have a question of, do these things actually have to be functions in terms of like following the vertical line rule? Because the examples they've drawn on the right in Figure 3.7, it's a little bit hard to tell, but it seems like no, I don't think they perfectly follow. Like, I wonder if these actually have to be functions or if they just have to be relations. Because if they're
Well,
just functions, it seems
the
restrictive. Sorry.
well, I
Go on.
think it's a function of time, right? Oh, sorry, no, but it's an integral, right? The action is some kind of time integral of the Lagrangian. So it doesn't matter if the x is a function, right? It doesn't matter if the x of t is a function. It just matters if the line integral of the Lagrangian of x and x dot over some. Does that sound right? A map from functions, but it does say a map from functions, in this case xt's. Oh,
And I wonder if they're just being loose with their language. Uh, I did just realize that the axes are flipped, so it would actually be a horizontal line test in Figure 3.7. But even then, I feel like
oh,
you would want the freedom to
okay,
do any
yeah.
path you want. I assume for a problem like
Yeah,
this.
okay. No, you're right, right? They play that game in this class where they flip the xt as to how we do it in math. So yeah, if you look at that picture, I think they're all functions of time, aren't they? I think they are all functions. Like if we do horizontal lines, they all look pretty good.
But I wonder if they would like I still feel like you would want the freedom to not be a function. I don't know if that's important or
Well,
not.
if t does stand for time, then I don't know. Can we go backwards in time again to get back to point B?
Can we go backwards in time to get to point B?
So if you think about the interval between time A and time B, and we're talking about going from starting at xata and getting to xbtb, we couldn't go past time B, could we? We would have missed point B at that point, I think.
Hmm.
Like if point B was I was going to give you $100 in a week, and then a week came by and I didn't give you the $100, and you asked me, well, where's my $100? And I said, oh, don't worry, I'm on a different function here, and I'm going to catch you back in another. I'm going to curve around back and come back to this point in time and give you $100.
uh,
I guess what I'm saying is I'm thinking of that maybe the arrow of time can only go one way in that picture.
okay. Yeah, and I guess you would only map like a single value of time to any x value you want. Like we're not double assigning time, so maybe that's what you're talking about.
Yeah.
Okay. And yeah, maybe I'm getting confused with
And
where
so
like you could
if
definitely
you drew
parameterize something if you added a third axis here and do some funkier path.
so if we drew a rectangle in that space-time plane there, right? And the lower left-hand corner of the rectangle is at xata, and the upper right-hand corner of the rectangle is at point B, xbtb, then I think these curves are allowed to go outside the left and right side of the rectangle, but I don't think they can go below it or above it.
Let's quickly pop over to the Excel draw to like draw that rectangle you're talking about. I mean
Oh yeah.
they do draw like two of these curves do go outside that rectangle.
Yeah, that's what I'm saying. They can go left and right, but I don't think they could go above or below it.
Oh, okay. And you're saying that as like a horizontal line test type of thing.
Yeah.
Um, okay, yeah, I think that makes sense. Dr. Cook, are you back? I see he's in the call, but he might still be getting
Yeah.
Okay,
And I'm here. I'm just chilling. I didn't want to interrupt.
no worries. Um, in case you're like, I know what point you like started hearing the conversation. We're talking about and the way that they've defined action as like a functional. Uh, we're talking about like if this x of t thing that we're mapping needs to actually be a function or a relation. And I think we've come to the point where it does indeed need to be a function.
I think, yeah, that's typically assumed, but I've never considered the more general case, and that'd be interesting to think about.
Yeah, I think I was thinking about relations because of like I was just imagining like an x and y axis or like a axes where you would want to be able to be a relation, but we're talking about x versus time, and that should definitely be a function. I think that's where my confusion was at least.
Yeah, no, yeah, there's physical reasons to want that, but as a purely mathematical question, it's kind of interesting. Yeah, in particular, you don't want like some arbitrarily weird function or relation. You're imagining, like at like it fails this vertical line test, like at 1x there's 2t's, or you is that?
Yeah, in the figure we're looking at exactly, they have like the axes flipped, so it'll be a horizontal line. But
Yeah, okay.
yeah,
Oh yeah, I guess yeah. Well, okay.
or we're talking about x as a function of time. So we definitely want time, the time to map to a unique, or we don't want one time to map to 2 points. That wouldn't make sense physically, at least.
Sure, sure.
Okay. Um. Okay, then what else does 3.5 talk about? Hey, Central. The variational
So you have to
principle.
derive the Euler-Lagrange equations. Have you seen those before?
First time. He doesn't derive them. He just says them.
Really? So I'm watching. Actually, Finbox, is this how you do it? You talk on Discord, but you watch the stream because there's like a little bit of a lag, right?
Yeah, there's a little bit of a lag. Yeah.
Okay, let me open the
I
book.
think
But I
he I
would.
think he yeah, I think he derives them on page 44, I think. He says something about like integrating by parts the action functional.
Oh,
I think that's a derivation. I'm not sure. I didn't read it that part super carefully.
yeah. I was under the thing that physics and depression did as being like a derivation of it, but this might also
Yeah,
be
no, and
another one,
yeah, he's
right?
deriving the Euler-Lagrange equations.
Okay.
So that's a differential equation that the Lagrangian will have to satisfy um, for the solution of that differential equation to be an extremum of the integral functional 335. So these are extremely useful. In fact, a good exercise I would do here, like if I were teaching a class, would say like, okay, use this to show that the shortest distance between any two fixed points in a plane is a straight line. Because you could write that as an integral functional. So say I have like points A, B, you could write um, the integral calculus like distance between them as an integral. Oh, Fizbo's wrote something. Yeah, the secret handshake. Oh no, I can't do that. I'll have to learn down their own. No, that is a good point. Yeah, this is a good watershed moment. Yeah, I think a good exercise. In fact, I would not be surprised if this was a Hartle exercises. So do you know this the Calc 2 formula for the arc length of a curve? It's like the square root of 1 plus f prime squared.
Yeah.
Yeah.
Yeah, so that's an integral functional where the functional
Oh.
that is like the path length of the function of the curve that you're putting between those 2 points. And so you could extremize that using the Euler-Lagrange equations, and what you should find and will find is that the shortest distance between 2 points is the line. So it's kind of intuitive, right? I mean, hope you kind of know that in your bones already, but it's a good check that the Euler-Lagrange equation is working as you think it should. So this would be S as a function of f of t, or f of
Oh,
like
yeah.
the functional augur. Yeah.
So you're saying
In
we
fact,
think of the square root of 1 plus f prime squared, we kind of think of that in the place of the Lagrangian somehow.
it is an example of a Lagrangian, I would say. I mean, not maybe remove. This is pure geometry, but
Yeah.
yeah. I mean, I think the Lagrangian was purely mathematical at first. Uh, maybe I don't know my history, but yeah, I would call this a Lagrangian as well.
Wait, isn't a Lagrangian? Well, the Lagrangian that we talked about is kinetic energy minus potential energy.
Yeah, that's for Newtonian mechanics, but mathematically, anytime you can write it, I don't know if Fizbo's correct me. I would call it this way. Anytime you can write a functional that's an integral of some other thing, the integrand I would call the Lagrangian, even in a
Oh,
generalized mathematical sense, beyond the context of Newtonian mechanics.
okay. Fispos agrees. Okay.
Yeah, in fact, if we go back to physics, what you'll find is what's the Lagrangian for special relativity? It's just that's the reason I'm giving this example, because the Lagrangian of special relativity is just the path length in Minkowski space, which has a pure math interpretation, if you like. Yeah, so
And
this might be a good exercise of trying to apply Euler-Lagrange equations to this. And I think what you'll probably find is f double prime equals 0, which is the condition of a straight line.
oh,
So the equation like 339, I think. That's the one you want. And also, that's really easy to remember. Okay, this is a cursed or scuffed way, as the Zoomers would say. But if you go to 339, the way I remember that is like, if the dt in the first term cancels the dt below the x dot. I mean, not really, but that's the way to remember it.
that is
Oh, that's
scuffed.
sneaky. That's sneaky. Yeah.
I mean, that's not really. It's kind of why it's true if you follow the derivation, but that's more or less just a mnemonic. So if you apply it here, the Lagrangian is that square root function. Yeah.
Oh, that's like a classic using the d by dx's as like fractions.
Yep.
I need to make those partials, but it's fine.
Another good exercise to do if I were like teaching this class, this Euler-Lagrange equations here, they assume the Lagrangian L depends only on x and x prime, which in this case is f, by the way. But you could imagine deriving the analogous Euler-Lagrange equations for a more generic Lagrangian, which could depend on f, f prime, f double prime, and so on. So what would the differential equation be required to extremize the action functional in that case? So if you see here, yeah, 335, he's assuming implicitly that L is a function of just the argument x and x prime. So that's the standard assumption for Lagrangian and Euler-Lagrange equations. But as a mathematical exercise, you could go through the derivation again. Let's see what the generalized Euler-Lagrange equations would be if you had L as a function of x of t, x prime of t, x double prime of t, and so on.
I think they make it. Oh, okay, yeah, I think at the very end of the chapter they say you just have as many equations. Oh no, I think that's a different thing. No, I think this is for more dimensions. You would have extra equations, but you're talking about more derivatives.
Yeah.
Okay.
So this is another way to generalize it. Yeah.
Fizzbuzz has to lurk. All right. Thank you, Fizzbuzz.
I would recommend trying the straight line proof, though. I mean, you're pretty much sure you got it all out. I mean, I guess it's like exercise 0 if you like.
So we're trying to extremize the arc length function.
Yeah. And this is important because it'll give you exercise notation. Here, the argument is f. and there that's x. So x of t versus f of x.
Right.
So you would want to do like dl df prime. Then yeah.
So this Lagrangian only depends on f prime, right?
Right. Yeah, that's a good observation.
And so we want to find like the delta S, I guess.
We
You
skip
can,
that
but
stuff, I think.
yeah, just jump to 339. You've got the hammered. You can just swing it.
Oh, just swing that?
So-
Okay.
Yeah.
Okay. And so our f prime is their x dot.
Right.
So dl df prime.
And their t is rx.
Okay.
Hmm.
d dx d dx.
So you need a time derivative or x derivative on the left. Yeah, and that equals 0. Because there's no, yeah, exactly.
Oh, I was like gonna do like just like one term at a time, I guess. I don't know if that was good or bad.
Yeah, that's good.
Okay.
No, that's good. Oh, I see what you're saying. Yeah, okay, fair enough.
He might be a couple seconds ahead than where he is on the stream.
Oh, true.
Yeah, I'm unfamiliar with this format.
Probably makes it hard to follow. Remix.
Also, I know it's kind of hard to do math while other people are like watching. I realize it's pretty brave of you, Don.
That's the entire stream. It is hard.
You know, in teaching, they say your IQ goes down by like 30 points in front of the blackboard.
I had a math professor say like he would make mistakes all the time, and he was always like cool about it. But like, every time you corrected me, he'd say like, okay, yeah, never do math for an audience. And now here I am.
Oh, you didn't take his admonition
Yeah.
to heart.
That's an annoying derivative. I think I did it okay though.
I don't know if you need the. Do we need the f double prime? This is where I'm gonna get
Oh, we're
confused.
doing it in terms of f prime. I guess not.
Yeah, you don't need the double f prime. F prime is the independent variable here.
Yeah, it's so confusing. See, that always messes with me.
Oh, and I guess we have to do a quotient rule to do the next derivative. Okay. Low D high. And this is with x, so we do want double prime.
Yeah.
Minus high D low.
You did cancel the 2's, right? Is that what you did?
Yeah, I did that mentally. This one we do get a double prime also. I think. Okay. I guess we can get a common denominator and hopefully make it look a little bit nicer.
I'm going to play the 2 canceller. Very important rule.
Yeah. This thing needs. It's going to be f double prime times that root plus f prime x.
I think maybe it'd be since this is going to be ultimately equal to 0, the denominator can be arbitrarily ugly. So I think what would be good is to multiply the top and bottom by that square root.
Yeah.
So the denominator will be the thing to 3/2 power, but that's okay because we're going to
Yeah.
set it to equal to 0. So what's going to happen is we care about the numerator 0.
Prime x squared to the 3/2. There we go. I think that's what we get after common denominator.
I'm confused. There shouldn't be any square roots anymore.
I guess just take out
Oh
that
yeah, that
first
should be a square
radical
root.
then.
Yeah.
Yeah, good. Okay, the numerator just becomes f double prime. So when that's equal to 0, we get f double prime is 0. So a straight line. Bada boom, bada bing.
Ah. Well, wait. Well, what about the this was just one term, right? I didn't do the dl dx or dl.
Right,
I guess
but
that's 0 though, isn't it?
Right, because L doesn't depend on
Okay.
f. It's a DLDF term.
So that's just f double prime over. I'm just gonna put parentheses. Is equal to 0.
This looks familiar. Where would I have seen this before?
Let me I want to rearrange
I
this.
remember learning calculus variations, but maybe I've seen it somewhere.
I mean, math classes, they like to do the Brookrista-Crone problem first. If you've seen that, like the curve that makes a bead fall the fastest between two heights.
Yeah.
Although I think this is the best example to start with because this is about as simplest as this gets. Like one nice thing that really happened here was that L didn't depend on F, so that one term was just 0. Yeah.
Double prime x equals 0 implies that the shortest distance between 2 points is a straight line. I should probably just type that and not write it.
So maybe it's worth emphasizing too here, the Lagrangian, this is a purely geometrical problem we just solved, had no necessarily physics input. So as Fizbo said in his comment, this is absurdly useful because this becomes relevant whenever you need to extremize any functional that can be written as an integral of some other function. So very, very general and useful.
Okay. Nice.
Yeah, I don't know why Hartle didn't make this an exercise in this chapter. It seems like an error.
He does give some like other type of functional. I don't know what this is supposed to be, but yeah. Yeah, it's gonna be the entire thing only has 6 problems for chapter 3, so
kind of odd. Have you studied special relativity before, or is chapter 4 going to be completely new?
I think both times that I've only both had a taste of special relativity from the E&M book.
Oh,
so only a
Lorentz
crash course.
Transformations.
Yeah.
Okay, that's pretty good. You're good. Yeah, you're chilling then. Yeah, it'll be good to see it again.
Okay, we'll see how we feel when we get to the actual things, for the actual problems.
Yeah, well, it might have been. I would have been epsilon concerned if this is your first time, but now I'm like epsilon goes to 0.
I already thought that I'd be set on chapter 3 of saying like, oh, Newtonian physics, I know those, and then I see like a Lagrangian, and it's like, oh no.
Yeah, I guess in a standard physics curriculum, you probably would have taken like intermediate mechanics before this course. Okay. But this book is specifically written to try to aim at students who have just done the first year. So he's teaching it to you because it's not necessarily assumed. So I think the fact that's new to you is kind of an expectation of the author. Which he died last year, I think.
Oh really?
My best friend was a PhD student in physics at Santa Barbara, where Pardo was a faculty member. I think he died last summer. Sad.
Damn.
Hmm.
I'm
Yeah, because I guess the first 5 chapters are all supposed to be kind of preliminary.
Right. Yeah.
Mhm.
So
Chapter
is there more of
4,
the text?
I'm
Oh,
thumbing
go
through
ahead.
chapter 4. It doesn't look too bad, but it doesn't look too bad, but who knows?
So for chapter 3, was there more of the text to talk about? Like that last example, did you guys do that? Work that out? Like while you were reading?
Yeah.
I didn't do it for myself, but it seemed understandable. It feels a little bit like I like the thing they did is they just kind of proved it's not two separate straight lines, right?
Mm.
Because they assumed it passed through another point. It went to one point straight line, and then from that point it travels another straight line to B. And I guess you
Oh,
can
I'm just
this
yeah.
way you can extend that argument to be for any like curve.
Yeah. Yeah. Actually, this might be another way of arguing that. Oh, okay. Actually, no. This is okay. This is like basically deriving Newton's first law from the mechanics of Lagrangian straight line. Yeah. Okay. I mean, this feels a bit artificial, but it's a good example, I guess.
Okay. Um.
I'm just noticing on screen that the PDF, I don't know if you can see that there were 2 other sides, 2 other lines in that picture from A to X and X to B.
Yeah, I have my own copy open right now. It looks like it's a sharper version than what Don's got up, but I don't have like subsection bookmarks. So I can
I
only
added
jump
those
from
in
chapter to
myself.
chapter. Yeah. Okay.
I couldn't
You
find a
ready to
very
start
clean scan of it, unfortunately.
Oh, I have a clean scan.
Oh,
Yeah, I'll just eat
yeah, if
that
you don't
into our
mind
group chat.
sending it, yeah. Oh, I did like this version because it was on archive.org, which is like a reputable site and not something sketchy.
Oh,
It'll
okay.
still be nice to
I
have
wasn't sure
that
then.
though. I still
Uh,
would like to have it.
Mine might have come from LibGen. That what
Yeah,
the sketchy means.
I don't care personally. I was just like thinking about like as far as like putting links out there, I wouldn't put like a libgen link out there, but and like the group chat is fine.
Oh, actually, it says the max file size for Discord is 10 megabytes. And this is 13 megabytes. Oh,
Oh,
maybe I can zip
well,
it. Let's see if I can zip it.
are you winning
Oh,
gravity and
it's
shit? We sure are.
now
Sorry,
it's
what?
11.6 megabytes.
Ah, I had
Uh,
the exact same issue. It's no worse if you can't do it. I know it's annoying.
well, it does look like it's higher quality than what you got on the screen, but then you'd have to add the things again. I don't know if that's worth it to you.
It doesn't take
Um,
that long. I don't know. There's always like Google Drive or something like that too, but it's up to you how much trouble you want to go through.
do you want to send me your email in Discord chat?
Oh yeah, that works. I mean, this email is just like listed on my Twitch page. Anyway, it's just this math at Gmail.
Okay, I'm using my personal email, so don't dox me,
Oh no,
please.
no. I probably just like
All right.
open up at after the stream. I won't like right now.
Sure. Are you ready to start problems?
Uh,
Sure.
yeah, I don't have too much else to say about the chapter. I don't think. So yeah, you can just pull in number one, unless we have a preference. Number one, and then I thought it might be helpful to. I only kind of skimmed what the question actually was. I thought it might be helpful to bring up these equations too. Okay. Free particles moving in an inertial frame xyz in the xy plane on a trajectory x equals d, y equals vt, where d and v are constants in time. Consider a rectangular frame x prime, y prime, z prime, rotating with respect to the inertial frame with an angular velocity omega about a common z-axis. What are the equations of motion obeyed by x prime, y prime, t prime, or x prime, y prime, z prime in the rotating frame? Sketch the trajectory of the particle. Sorry, what?
What do you got? What do you got copied there below? 1, 2, 3. What is that?
Oh, I just thought it might be helpful. I don't know if it actually is, but those are just
Oh,
how inertial frames
okay.
can differ. But it might not
Oh,
be helpful
yes.
because it won't be inertial, the rotating one, right?
No, I think I mean the second one plays phi with omega t,
Okay, yeah, that makes sense. Hey, Phobos.
and then the second time derivative of the unprimed coordinates is 0 because they're inertial, right? Uh, oh, actually, well, no, sorry, they're giving us the motion, and we want to see what differential equation they satisfy. Okay, yeah, so I think you want to use the second one. Yeah, and phi equals omega t.
Yeah, that feels right.
X, Y, Z. So this frame is moving in the Y direction. Or wait,
Might be better
no.
to draw it without a z-axis because I don't think z is going to play in here.
I drew it in because the rotating frame is rotating about the Z-axis.
Okay.
I don't know if that's. I don't know. I might regret this. Hey, Lo, I'm good. How about you? So the particle is moving. It has a constant x value, and y is moving in the y direction with velocity v. Then we have x prime, y prime, z prime about a common z-axis. So are these origins the same?
Yeah.
I guess we can make them the same. So I'll draw the other frame in green. Z prime, X prime, Y prime. It has an angle, the X prime makes an angle omega T.
Right.
With the regular X axis. So we need to, I guess,
I guess you
find.
just plug in
Oh, yeah, I guess we can just kind of use the number 2.
the d and the vt could be plugged in again as well, I guess.
Yeah, so phi goes to omega t. You plug in x and y that are given, and then it's asking for equations of motion. So of the well, I would interpret that to me, it's asking for the differential equation, but a good first step would to just solve for what x prime and y prime are as a function of time.
So cosine omega t times our regular x value, which is a constant d, plus sine omega t times the y coordinate, which is vt. Hopefully. Then y prime of t is minus sine omega t d plus cosine omega t vt. And then z prime is still z.
Yeah, I think we can just kind of forget about z for now. So the next thing I would notice before going farther is just that the unprimed coordinates, x double prime and y double prime, are both 0. And that's an expression of Newton's law in this case. It's a free particle experiencing no force, so its acceleration must be 0, which means it can move with constant velocity, but no, it can't change that velocity. So x double dot and y double dot are both 0.
Oh, but then x
And
double
now what
dot
you're gonna
prime won't.
exactly, and same for y double. So that's what I think it wants you to do. Take the double time derivatives of x prime and y prime, and you'll see, even though this is a free particle, there's a non-zero acceleration because we're in a non-inertial frame. So what you're finding is a fictitious force.
Nice.
Ooh,
I would
okay.
suggest using dots over the variables for time derivatives.
Yes.
Right. Yeah. I noticed that. Yeah.
It's a really nice notation. I started using it a while ago. I don't know where I first saw it, but I just feel like it's a nice way to do it. If you're differentiating with respect to time, just write a dot above the letter.
It feels quicker, right? Even though like prime
Yeah.
isn't particularly onerous either.
And it doesn't
But
get in the way as much either.
yeah, that's true. Actually, you don't shift the arguments, right word.
Product rule. Uh, do. Ugh.
Why did he give us a D instead of an L?
Yeah, I noticed in Don's y prime equation, this is the sine omega t d plus. That d plus looks like a dt
Oh,
in my
yeah.
mind. But yeah, d can get annoying.
Okay, I think I did that product rule okay. I guess I'll just go straight to x double dot. Annoyingly. Minus d.
You could group the first two terms if you wanted to. I don't know if that is a good idea.
I could, yeah.
Don't worry, I'll just sit here and backseat drive, you know.
It makes it look a bit cleaner. Okay, then this derivative is going to be omega v minus d omega cosine omega t minus product rule. Ugh. I guess I'm doing the cosine first. Plus v omega cosine omega t. And we could group that again.
Oh, this feels kind of Coriolis to me.
Yeah, I think. Yeah, that's what I expect too. You got 2 omega v with the cosine, don't you?
2 omega v?
That I think that, don't you? First and third terms.
Oh, we do have 2 v omega cosines, don't we? What am I doing? Oh, if I, yeah, I need to bring, I didn't bring that inside the parentheses correctly. It would need to leave the omega at the door. So that becomes a 2v. Yeah, I think that's right. Okay. I think that's our acceleration in this rotating frame. For x, I guess we can do the same thing for y. Y dot prime.
Is there a shortcut here? No, maybe not.
Oh, just like using the form of the first one. I don't know.
Where's the link to
I'm
the?
trying to think, just change the sines to cosines and cosines to sines, but
The link is
I'm worried about
Oh.
negatives.
I found it.
okay.
I didn't realize the chat had a. Sorry, I didn't realize the voice chat had a text chat component to it.
It's a really weird thing. I put it there because I don't want the link to be like just publicly out there. Because people have trolled me before, so
Yeah, somebody will, come in and start drawing rude pictures on it or something.
yeah. It's happened.
Which would be funny, but still,
Yeah, it would be funny. I would want to like encourage that to happen all the time, though.
Okay, I think we're not going to be quite done after we compute the second derivatives because it's asking for an equation of motion. So I think what it wants you to do is to like write this as a closed differential equation. So like when we have x double dot prime and y double dot prime, there's going to be a bunch of sines and cosines. But I think you want to re-express that in terms of x prime and y prime. So then you found the differential equation that x prime and y prime satisfy. Analogous to.
Oh. Okay, so we're gonna have to search for x dot and just x inside our x double dot. Okay.
Are you using an iPad, Don?
A
Or
tablet. Yeah.
Okay.
I used to just use my mouse, though. It eventually started to hurt my wrists, though. Why do I have a parentheses there? Okay, this is another product rule. I take the derivative that first. So we get a minus v sine omega t. Minus omega d omega plus vt cosine omega t. And then we can group that. A little more. These are both negative. I don't know if I like that. Okay, assuming I didn't make a mistake somewhere, I think I got y double dot here.
I think x double dot and y double dot should pretty much look the same, except sines and cosines should be reversed. So
These don't look the
something
same.
might have happened.
Yeah, we did. All we did was kind of switch sine and cosine between x prime and y prime. So why is something
Would
weird?
this one here be a cosine, maybe?
Oh, I didn't take. Oh my god. I always do that. I forget to apply the chain rule like that. Okay, well that
Wait, so Don, are
screws up
you
everything.
on the in the Discord chat room on your tablet then?
Oh no, my it's not a standalone iPad. It plugs into my computer directly, so it's not
Mm,
like its own
mm,
device.
okay. Hmm. I think how I should do this. I have my iPad here.
Oh, I think Penson has the same issue. I forget how he fixes it though.
Maybe I can just share this link to my iPad, so I don't have to go through
Yeah,
Discord.
if it's easier, I can like message it to you too.
I should be able to just airdrop it.
Okay.
Figure this out.
Okay, is this derivative better, or did I make the same mistake twice? No, I think it's good now, the first derivative. Okay, and so that, in theory, only messes up the first thing, right? No, I think it messes up everything.
I think you lost an omega in the last term.
I do need the omega there, don't I? I agree.
I'm just cheating off your previous work for X dot, trying to make them look the same.
Hey, this is one where I wouldn't mind just, or if I knew how to do it properly, just using like Wolfram Alpha or something, but I don't want to make it work with all these constants. Okay, I'm just gonna, at my own risk, proceed with taking the next derivative. Yes. Take the derivative of the first part first. Minus. Omega
Do you use this in browser? I mean, this is kind of hard to work with. Like, I get to do two fingers to pan.
Yeah, 2 fingers. Yep.
Yeah, okay.
I use the hand
Where does
tool.
that
I just
count?
have it on a button to pan.
Okay.
Okay, I think my derivatives are okay. Let's group omega d omega minus 2v sine omega t. Oh, it's complaining. Omega squared vt cosine omega t. That looks more like x double dot.
Yeah.
Yeah.
Looks good.
It makes sense if they're off by a sign or by a, or like the trig function should definitely be reversed. And one of the signs being reversed seems reasonable enough.
I bet you this is somehow like multiplying by I.
Oh, probably, yeah. Okay. So Cook was saying that we should try to turn this into a differential equation if we can.
Yeah, equations of motion, and then it wants the trajectory. I was wondering what it's going to look like.
That does that.
Spiral, maybe.
Yeah.
If I was drawing a line, at a constant speed, and then I started spinning the paper I was drawing on. It feels like that would have to be a spiral.
I like that visual. It does have a spiral feel.
We could probably work that out by like squaring both sides. Because if we did x prime squared plus y prime squared, we would get, yeah, we would get d squared plus vt squared, v squared t squared. So how does that help? If it was polar.
Oh yeah, there should be some cancellations there if you square them. There should be some Pythagorean identity stuff. Is that what happens?
And I could think of this as like r prime squared, couldn't I?
Oh, do the cross terms cancel?
I think so. Yeah, they're gonna cancel.
Okay. Wait, so is r equal to like 1 plus theta? Is that a spiral?
Yeah, some kind of spiral. There's lots of kinds of spirals. That's got to be some kind of spiral.
Oh, it sure is. Hey, Jasu. And I guess we technically have a square root and a squared here, right? Plus theta squared. That's still a spiral, though. Interesting.
So the trajectory looks something like that. Okay.
Oh, I didn't see what Cook was doing up here.
I think this is just a kind of a trick to simplify it. You can think of
Complex
complex plane
numbers.
rotating. And then I'm using the fact that z double dot is 0 by Newton's first law, the unprimed coordinate inertial.
Hmm.
So then we can split this out again. I should get the same thing as you do, but I'm worried I got the z dot there. Well, actually, I can rewrite that this way.
Hey, Tree, I'm back.
Okay.
Oh, nice. You got it in complex variables.
Coriolis.
Centrifugal.
Omega squared. Yeah, omega squared feels centrifugal.
It's directed radially outward along z prime. So yeah, so this is a spiral because, well, actually, I guess I don't really, I haven't thought about Coriolis in a while, but a spiral seems reasonable to me from this. But the trick was actually, so this took me a second here, was here, I'm gonna highlight in blue. I had this unprimed appearing in my differential equation I was trying to get for the prime variable. And so I had to eliminate that using the prior equation here. So there was some peanut butter in my jelly. I just wanted jelly. So I had to get rid of the unprimed. But yeah, so okay. And so what this I here is saying is that the Coriolis is 90 degrees from the, it's proportional to 2 omega times the velocity, and it's directed 90 degrees from the acceleration. So it, well, Coriolis is tricky with signs, but that I there means 90-degree rotation. I'm sure, is this what you found? How far along did you get?
I was struggling to find the differential equation.
Yeah, so we can, this is it in a compact form, but we can split it apart if we equate the real and imaginary parts.
The grouping may not have been a good idea if we went for the differential equation in our work, actually.
I was thinking of grouping because I just wanted to square things and try and cancel out all the sines and cosines.
Oh yeah, it's
But
something nice
yeah.
for the polar coordinates. It is a little hard to see with the non-complex because I think we would get some cancellations, or like we need to. There's going to be some type of cancellation, and I can't quite see it.
Well, it's going to be tricky because the second derivative, you have to write it in terms of both the primed and unprimed. Like if you look at the first blue equation, the x double dot, which you calculate prime, you have to write that in terms of the first just x prime, but then the y dot prime. So this is one of those things where like if you knew where you're going, you could kind of work back. But maybe that's what he intends. Like that you kind of realize this choreo. I have to read the problem again. What are the equations of motion? Yeah, okay.
I mean, I imagine you could just you know that like you could try and figure out like what just the like x prime term is, and then figure out what the other term must be or something like that. But I think it takes a lot of like playing around.
So the centrifugal is pretty easy to understand. There's like a radially outward directed force proportional to omega squared. That's why there's both pluses there. The Coriolis, I mean, this is like 2 omega v, but the signs and the flip, like the y appears in x equation, the x in the y equation, that's reflecting this 90 degrees from the radial direction. So it's like tangential, and its magnitude is 2 omega v. Oh, okay. And then actually we have some things that don't we? So he gave us, what did he give us? X is D
Yeah.
and Y was, what was Y?
VT.
VT.
VT. Okay. Oh, ooh, gross. Okay. How do we eat this in here? Oh, actually, no, this is going to tell us what, yeah, okay, so we can solve this in general. Okay. So this is going to tell us that Z. Okay. Okay. let's just plug in here. So z prime dot. Shoot. I don't want to do this anymore.
It's
It's just so annoying.
okay if you don't want to.
No. I'm just bitching about it. The math gods will be displeased if we quit. I don't want to tap out. I just want to complain while I do it.
It does seem like complex variables lend themselves to rotational stuff like this, though. I do like seeing that.
Oh yeah. Oh yeah. Actually, maybe it'd just be better to plug in.
Hey, Shecker.
Well, shoot. Yeah, because we want to solve this, right? So,
Well,
so we really have to just.
didn't we already
keep it
solve
in.
it? Or that's what we came from, right?
But we want to solve the differential equation. Oh, actually, shoot. I just got enough. So, okay, what I was saying is that we want to plug in x equals d and v equals, or y equals vt in here. And so this is the general differential equation, but we want to solve it for the given motion in the unprimed frame. So that yeah. Or actually, maybe you did do that. Did you already do that?
Or
Yeah, I
I
guess
thought
you
that's
already
what we
did that,
came
didn't you?
from, and we're just kind of constructing the differential equation from the answer.
Oh yeah, you're right. I'm sorry. Okay, but what you plotted earlier, was that the x prime and y prime? Did you plot that?
I did
Should-
like a version of it in Desmos. It comes out to be a spiral.
Okay, you did do that. Okay, then I'm happy with this. Is that? Yeah, I feel like this is what I should. Okay.
I couldn't
Yeah.
get like D and V
I
in
have
there, but Hemlock showed that in polar coordinates, it's just basically root 1 plus
Where'd you
theta
get-
squared.
Well, don't you want to do? Where's Finbox's work? Oh, here. Oh,
In
nice.
red?
Okay, so
Yeah.
that's what you plotted. Got it.
My
Yeah,
work,
you
my
plotted.
work was with like one line. I don't feel like I really got very far, but it seemed like that. So that told me that the radius in the primed frame was the square root of, basically the square root of t squared. So it should be, yeah. So it
Yeah.
should go out kind of linearly with t in the long run.
Can you parametric plot?
Yeah, we can do those in
Desmos?
Desmos.
I mean, you should get the same. You should get the same thing. I just was curious whether that has parametric plot in it.
It does. I'm going to treat all the constants as 1, though. Cosine t. That's not it. Cosine t plus t sine t. Oh, really, Desmos? And then
Yeah. So
that's
if v were
x.
0, it should be a circle, right?
Yeah.
Because then x equals
Oh,
d,
yeah.
you just rotate that. Yeah. And so what the v does is it lengthens that circle every time.
T, is that it? Yep, and then t needs to go from 0 to like 12 pi. Get rid of that. It's not the same spiral for some reason. Oh, because the constants aren't going to line up, I assume. It is still a spiral.
Well, as v goes to 0, you get a tighter and tighter spiral. And if v is very large, I think it should start to look like a straight line.
Where is v in this? Okay, I can insert v. Let's say v can go between 0 and 100. So yeah, just a circle for v equals 0. Ooh.
And I think for v very large, it should be.
Yeah, for like 100, it starts to straighten out. For like 1,000, yeah, it's straightening out. I assume
Because, like, yeah,
if we
you're
zoomed out
loosening
far enough, it
some,
would
yeah.
come back around. But
Yeah. So V has units of meters per second, and D has units of meters. So you can't compare them directly. Like, it doesn't make sense to say V is large compared to D. So the third parameter we need here is time, and that's basically how long do you let it, how many times do you let the spiral or like the disk rotate. So it's the interplay of those three things that make determine what this looks like. So when you have a certain view frame, like limits, you're implicitly assuming some time. Yeah, I didn't explain that very well, but hopefully it made sense.
just that it's hard to compare like the polar version to the parametric version. Oh,
No,
that's
just that
hard.
like these two comparing V and D, they have
Oh, okay.
non-compatible
Yeah.
units. So yeah, you're right. For any, even for very large D, if you zoomed out enough, that means watching enough rotations, you could start to see the spiral. But I'm just pointing from a physicist standpoint. That means you're introducing the third variable T. So what you're really comparing is VT and D, which have compatible units. Yeah.
Okay.
Something new in my life, guys. I got a girlfriend.
Oh.
And we have a hot date tonight, so that's why I'm gonna have to dip out on you.
All
Well,
right.
have fun.
Good luck.
Yeah, as fun as Hartle and Finvox and Don are, I have a hierarchy of values, let's say.
Yep, yep, I hear that.
Well, enjoy.
Are you gonna try to do all 6 problems from chapter 3 today?
Oh, not today. We can go on to chapter 2 or to number 2, but we've gotten through one problem in an hour and a half, so we're not going to do them all today.
Okay, all right. I want to see you guys get to the actual physics soon, because even the spectral chapter 4, I mean, that is real physics, but it still feels preliminary, I guess. That's necessary. I'm just like chomping at the bit. That's all.
Okay, I mean, I was planning to just do like 2 weeks per chapter, but if you want to call one out, it's just like only spend 1 week on it, then feel free to do that.
Let me look at the problems before I go. Yeah, I would. Let me see here. Let me look at these. So 1 is good. Yeah, we did that. 2 is very good. I would make sure you have a good understanding of that. 3, I mean, that's fun as a physics problem generally, but not super relevant. Find the gravitational potential inside and outside of sphere. I mean, so 4 should be, you should remember the result maybe from E and M.
Yeah, I assume it'd be the same.
Yeah. 5 is good, very good practice. 6, I don't know if I would. I mean, it's someday do it.
The letter ones for last. Yeah, if we have time.
Okay. Yeah, I would cut 3 and 6, and maybe even 4, or just do quick 4. But like 5 is good practice for sure.
Okay.
Oh yeah, actually, you should probably recognize what that is. Yeah, because if we compare that T minus V, so you have the kinetic energy term V squared there. And the second, that's like a spring, but with negatives.
K equals.
With the sign is wrong, so it's actually like you're on top of a hill. The action is T minus V for mechanics, so this is like a negative x squared potential. So it's like you're on top of a hill. So as soon as you start to fall off the hill, you get faster and faster away from the unstable equilibrium point. So anyway, I expect actually this should be, the solution should be like for a spring, you have a linear combination of sine and cosines. This is the negative inverted, it's like a negative x squared potential. So the solution should be a linear combination of hyperbolic cosine and sines, like Koch and Cinch. And that corresponds to like just accelerating away and away from the x equals 0 unstable equilibrium point in this case.
Oh, okay.
A hyperbola instead of a circle.
In I guess the XV plane, something like that.
Yeah.
Yeah, so there's not really 2 dimensions. There's only 1 dimension of space here. But it's like the more you stretch the spring, the stronger it pushes you away.
Oh, it's a reverse spring,
Like a
I
negative K.
guess.
Yeah. Yeah. Okay. I gotta go.
Okay.
Nice
See you
chatting
then.
to you guys.
Thanks for
Bye.
being here. Bye.
Yeah. It's like a bizarro world spring.
Yeah. At least for today, do you want to just look at number 2?
Sure.
Okay. Got 20-ish minutes. I'll bring it in down below.
I think I saw, because I watched a video on general relativity yesterday with what's the guy's name? Leonard Susskind.
Mhm.
And I think he did something similar to problem 2. So I think
Okay.
I have an idea of attacking it.
Total motions are non-invariant in a transformation frame that's uniformly accelerated with respect to an inertial frame of Newtonian mechanics. So I assume we would do the same thing as last problem, except we have an accelerating particle?
An accelerating frame,
Or,
I guess.
yeah, or I guess like, yeah. Like,
Am I
could
reading it right?
could we take the same setup
Yeah,
as last time, but instead the particle, I guess it would be like y equals like 1/2 a t squared or something, is what I'm imagining. Like, one of our coordinates should vary with t squared.
Yeah, so maybe like equation's 3.5 there. But instead of x minus vt, we can have x minus at squared or something.
Yeah. That seems like a good place to start. You just keep it 2-dimensional, I guess. I mean, it would be as simple as just taking 2 time derivatives and not getting 0. That book was making a. I'm going to say 1/2 just for the sake of the derivatives, but I thought so. Like, or at one point, this book was saying that like, it was showing that the second derivatives are all 0, and that's Newton's first law, I think. Yeah. Equation 3.2 is the expression of Newton's first law. Inertial frames can be defined as Cartesian reference frames for which Newton's first law holds in the form 3.2. This is on page 32.
Yeah, so if we take the second derivative of this one, we get. Yeah, so if you differentiate that equation twice, you get x prime double dot equals x double dot minus a, right?
Yeah.
And so if x double dot is 0 from the inertial frame, we just get, right, x double dot prime is minus a. So then, okay, well now we can. Should we have used the letter A? Maybe we should have used a different letter, because now I want to use F equals MA.
Oh, we can call
Maybe
it
we should have used.
alpha, or that's angular though. M. I don't know. I mean, we could say G. I don't know if that's. That might be
Yeah, we could
dangerous.
say G.
Okay.
Actually, that seems like a good choice, right? We could have our second frame be the same as the first frame, except we drop the second frame out the window.
I like that
Yeah.
phrasing. Yeah.
Get a red pen. I don't know. Why am I drawing this? We don't need this, right?
I'm just seeing where you're going.
So kind of like this distance here is 1/2 GT squared.
Should the other axis be y or t? Or, I mean, I guess for the sake of the distance between the frames in the x direction, it doesn't matter. Maybe, actually, no, I guess that's fine.
The pencil was really thick. I don't know why. Nope. No, here. I got an iPad and I bought an Apple Pencil last week. I got to learn how to use it. So maybe if I use it, I can write better.
Oh, yeah. Some of the Scaldra is a little
now if we-
unresponsive too. Go on.
I was going to say, so if we had a particle in the, let's say this is the particle P, and what do we want to say now?
I guess in your analogy of dropping one of the reference frames out the window, it would be like us watching a ball as we drop it out the window versus us being on the ball, looking back up where we got dropped from. I think that's what's happening.
Yeah. It doesn't work, does it? Can I change this to a plus? If I'm in the X prime frame, the X coordinate is going to be, my X prime coordinate should be bigger. If my X prime frame is falling, then the X prime coordinate of point P should be bigger than the X coordinate.
This always hurts, or this is always weird to me. For how you've drawn it, the x prime should be a bigger number than just x.
Yeah, let's make this a plus.
Yeah, we can do that.
So now if particle P is at rest in the X frame, then if I'm in the X prime frame looking at it, I see it accelerating upwards, don't I? So how do we write this? Because I want to use F equals MA and I want to say, okay, so can I say this? I don't know if this works. So this has mass M. So F equals M X double dot equals 0, right? There's no net force on that object in the X frame.
Okay, yeah.
But now if I go to the X prime frame and I try doing F equals MA, I see F equals M X double dot is MG.
X double dot prime?
Thank you. Yeah, X double dot prime.
So we now see there being a force.
Yeah, so because we dropped the second frame out the window, the person in that frame sees that particle P as if it's accelerating upwards with
Yeah.
acceleration G. So
It's another fictitious force like we got with the
Yeah.
last problem.
Yeah, right. Fictitious force, right? Newton's laws of motion are not invariant under a transformation to a frame that's uniformly accelerated with respect to an inertial frame. So if they were invariant, what do I mean if they were invariant? We'd still have to see a zero acceleration, wouldn't we? Or a zero, sorry, zero force.
Yes, I believe so. We started with the laws of motion saying that the acceleration is zero. And after this transformation, the acceleration is not zero. So I think that's a variance.
Yeah.
I assume that's what they mean by that. Okay,
So the question says, what are the equations of motion in the accelerated frame? So is this here just all we need for our equations of motion? Just like x prime double dot is g?
that was my thought, yeah. This seems almost too straightforward, but I think that's just the answer.
I feel like maybe that's the answer. I'm pretty sure this is what Leonard Susskind showed the other day when I was watching it. I remember he came up with an extra mg term.
I could check the solution key here. Unless you want to think about it more.
No, I guess we're good.
Okay. Number.
I mean, we did it fairly simply. We just sort of assumed that the
Looks like they do the
two
same.
frames are just accelerating along one of the axes, but I feel like that's the way they usually do it in these problems.
Yeah, okay. They do basically the exact same thing. They maybe do it in reverse. Or like we swap the primes and unprimes, but that shouldn't matter. Yeah, I think it's
Oh,
yeah.
I think that's why I changed the sign. The signs always mess with me. So basically we got the same thing they got, but like you said, we've got the prime and unprime just reversed. I think that's fine.
Yeah, I assume you could always rearrange one to get to the other. There's like, yeah, we just did the other direction of the equation. Okay.
Or maybe in their case, they didn't drop the frame out the window. They sort of accelerated it upwards on a rocket ship or something.
Maybe, yeah.
All right, well, cool. Have we got time to look at another one or not?
I mean, 10 minutes, let's see.
We could discuss it, just discuss it if you want. I mean,
Yeah, 4 and 5 are the two. Cook said that 4 should basically be the same thing as like an E&M problem. We could at least start on 5 since that's the more important one. Or we could just try and knock 4 out quickly. I don't know. Sorry. Or
I feel like neither one of them should be too hard.
Okay. Okay. If you're feeling confident, then I guess let's do 5.
All right, great. Let's try it.
Poincare transformation, Newton's laws? I'm not sure, underscore. I haven't heard of those at least. Okay, we have this functional to contend with. Let's find the curve x of t satisfying these conditions. X is 0, 0, x of t is 1, which makes Sx of t an extremum. What is the extremum value Sx of t instead of maximum or minimum?
Oh, we got to hit this with the Lagrange equation.
I guess so, yeah.
So that thing in the square brackets is our Lagrangian.
Yeah. So this only depends on x, interestingly. So the first term just zeroes out anyway. Because that's
Don't
x
we want to
dot.
think of the first? Don't we want to think of this as x? So this up here would be x.
Oh, sorry, it does
I'll
depend on x dot.
undo. How do I undo?
Control Z.
Control Z, thank you.
Sorry, yeah, and I suppose that does depend on x dot. They're just mixing notation here.
Because I want to think of this as x dot squared, really.
Yeah, that was throwing me off.
So is it all right to just say L equals x dot squared plus x squared?
Yeah, I think so.
Okay.
Hey, color cone. So then, what's our Euler-Lagrange with this?
Swing that hammer.
Yep. So
Hit it with Cook's hammer.
yeah. You get 2x dot plus 2x equals 0. Hey, McKenna. Lagrangian? Yeah. Okay, and then that becomes minus 2x double dot, I guess. Plus 2x equals 0. And now to have an ordinary second order differential equation.
Mm-hmm.
We can get rid of our 2's. Okay. I guess we'll do this the old-fashioned way. Characteristic equation. R is plus or minus 1. Oh, this is where the caution sensitive. Okay, I guess I can see where it's probably going to come from now. C1e to the t plus C2e to the minus t.
And then we got two boundary conditions.
Yeah. X of 0 is just C1 plus C2 equals 0. X of capital T is 1. So first one, C1 is minus C2. Plug it in down here. And we're solving for C1. That's an annoying value for C1, but it's what we get. And C2 is just the negative of that. So I guess we can reverse the order of the denominator. So what does x of t look like now? E to the small t, or e to the big T minus e to the minus big T. I did get thin. Plus e to the minus t over e to the minus t minus e to the t. I wonder if there's a better form to write this in.
You could write it as get a common denominator and subtract those, maybe.
Denominator. Maybe, yeah.
Well, if t is 0, we definitely get 0, and if t is capital T, we get 1. That looks good.
Underscore is saying that it looks like sinh of small t over sinh of big T. And I think that sounds right. Because the over 2's would cancel.
The 2's cancel.
Yeah.
Okay. Sinh.
So I guess this is our extreme value. Either one of these last two steps.
Oops, what happened? Sorry, I lost the Excalibur here for a second.
Oh.
Nope, I'm still here. I'm opening a second one. Why?
We can get back in.
So it's basically a constant times sinh of t.
Yeah.
What's the derivative of sinh? Cosh, right?
Oh, I don't remember if there's a minus or not.
I want to say derivative of sinh is cosh and derivative of cosh is sinh. I think that's how they work.
Oh yeah, there is no sign flipping. I believe it.
So if we plugged it back into our Lagrangian, we'd get sinh squared plus cosh squared, which is what?
Yeah.
It's not 1. It's what is sinh squared plus cosh squared? Is that minus 1?
Does Paul not have this one listed? For shame. Oh, cosh minus sinh is 1. Is cosh plus sinh anything? I'm just putting into Wolfram Alpha. It's not anything, it's just a function, apparently. Let's say it's cosh, your cosh of 2x. Underscore is wondering if heuristically you could differentiate. I mean, I'm wondering about like this maximum or minimum thing. I don't know if that's the thing you're talking about. Hey, Danish.
That's what I'm wondering about too.
Differentiate s with respect to x. I think that's what we're going to have to do to find out the second question or something like that.
Let's just go up to the top and plug it back in, right? So let me just call it I'm not going to put the, I'll put it here. I want to write that 100 times.
Oh, you want to actually compute this integral?
Yeah, why not? Can we do it? Is it hard? Wait a second. Is it going to be
Uh,
hard? I don't want to do it
No,
if it's going to be
I
hard.
think it'll be easy because sin squared plus
What
cos
is
squared
this?
is cos 2t, so that'll be quick to integrate.
Cosh 2t, is that what you just said?
Yeah. And the integral of cos is just sinh.
So 1/2 sinh, I guess.
Yeah.
Sorry about the handwriting here.
Nah, this is fine.
So on sinh of 0 is 0, right?
I'll verify that. I think so. Yep.
All right, this seems like something that should still reduce a little bit, maybe.
Does seem like that.
That's hard for me to read my own.
I'm just shamelessly using Wolfram Alpha. You can apparently make it 2 coth x. I don't know if we prefer. I don't know if I prefer that though. Nah, it doesn't seem like it reduces that nicely unless you want coth.
Well, that's our extreme value anyway.
Right.
Doesn't seem like this would be a max or a min. What we're doing is we're taking the square of the function plus the square of the derivative and integrating that.
Cook was
I know I've
saying,
heard it called the principle of least action, but then it's not always least. It's just extreme action.
yeah.
And it can be maximum as well, or it could be like a saddle point, it's said in the chapter.
And Cook was saying it's like being at the top of a hill in terms of the potential, at least. I don't know if that. Maybe I shouldn't interpret it as a maximum for this, but. Trying to figure out what happened if it would deviate slightly from the path. It's kind of hard to imagine, though. Because we want to know if the action increases or decreases if we do that.
I know shine looks something like this. So if we had These 2 points.
Clarkman is saying to argue that the functional is convex and the Lagrangian being convex means it wouldn't be that hard. I think convex is like concave up in the terms that I'm familiar with, I think. It's just so hard to think about when the input is a function. It kind of breaks my brain.
Yeah. It does feel like if it's either a maximum or a minimum, I mean, there's no way it could possibly be a maximum, is it? Could it be? Because I mean, we could let this thing, if we want to go from this point to this point, we could skyrocket down to like -1,000 and then come back up, and that would give us a much bigger integral here. Because we're squaring the derivative and we're squaring the value of the function, so
Okay, yeah. I was trying to think of like how like it does feel in a way that it's like monotonically increasing, but it doesn't. I haven't quite like I don't know quite how to define that with like a function like that, but I think that's basically what I was trying to put into words. Underscore says it's an extremum, so either max or min, integrating positive integrand, so its minimum has to be 0. So this has to be a max.
that's a good way to think about it, right? Both things are being squared, so it's non-negative, right? Yeah, both terms in
Wait,
the
underscore saying
integral
this has to be a
are
maximum
squared.
though? Now we have
I think it
conflicting.
should be a minimum.
Hmm.
Yeah, I think it's a minimum, but I don't really know how to argue it other than just saying we're integrating a function that's made up of a sum of squares. So we're integrating something non-negative. So if we can vary those non-negative terms, the only chance we have is to make it a minimum.
I guess so. Yeah. I'm trying to think of an example that we might have seen that has a maximum, but I think we've only ever looked at minimums. Like with our arc length, we were doing a minimum. And the example problem was a minimum. Underscore made him sick with the maximum, maybe. Yeah, it does feel like we could make this thing arbitrarily large, but not arbitrarily small. This S. Or is arbitrarily negative. We can get it to be 0, or it has the vibe of a minimum. I think I agree with that.
Yeah.
I think I want to check the answer though and see what rationale they give.
Okay.
Underscore agrees it's a minimum. General solution is a linear combination of sinh and cosh. The solution satisfying the initial conditions is sinh small t over sinh big T, as we found.
Nice.
Value of the action is extreme can be found by doing the integral directly. Is most easily computed by integrating 2 by parts.
They did go to hyperbolic cotangent.
It did, yeah.
You know, I think the sine function works the same way in hyperbolic as it does in regular. So if you got a double angle, I think you can. So I think sinh 2t is the same as 2 sinh t cosh t, and then we could have done it that way. I'm pretty sure that works that way.
I don't see how we're integrating 2 by parts, or I don't see how that's possible, but...
Well, the derivation they gave in the textbook was of the Euler-Lagrange equations was integrating that action functional by parts somehow. So maybe they're doing the same thing here.
Oh, maybe, yeah, when they did it generically.
I feel like what we did by plugging it back in was super easy too.
Yeah, it's a lot easier to follow, at least. The second term vanishes because of Lagrange's equation, sure. So the action is just cos t, or parallel cotangent, as we said. The extremal path, the argument of the action is positive for any choice of x of t, and can be made arbitrarily big by choosing a wiggly path with big x dot. The extremum, therefore, cannot be a maximum, but must be a minimum. For example, simple path x star equals small t over big T satisfies boundary conditions and has action that, which is greater than the action in the 3.
Ah, straight line. We could have thought about that.
Yeah, that's probably a really handy example to have for these types of problems.
I was kind of thinking about looking at a straight line, joining the points.
Just as a quick verifying, let's look at hyperbolic cotangent and I guess.
Yeah, underscore, that's a good idea. Yeah, that's exactly what the textbook said. Yeah, make it wiggly. Yeah, I was thinking of just taking it down to negative, 1,000 and coming back up, but you could just keep it almost the same, but just wiggle, wiggle, wiggle. Yeah, I like it.
Okay, yeah, this alternative path, or the other thing does have a greater action. It's like a check mark.
Check mark.
The action for this, my x here is capital T. So I guess as long as capital T is big enough, the action is indeed greater.
Nice.
All right.
Eagle
Hey.
just came in.
So we just wrapped up the problem, I think, equal, but this is what we were working on right here, involving functionals.
It was a problem for finding least action.
This is part of a reading group that we're doing on Saturdays on general relativity. We're pretty early on, just kind of laying the foundations here. So we kind of did the important problems from chapter 3, I think. I don't know, like, how long is chapter 4? Would we theoretically want to push to just do chapter 4 next week?
If you want. It's actually quite a bit longer.
It is 47 to 71.
25 pages, roughly.
24. Actually, well, more. That's just the contents. I wonder how intense it can be, because I mean, I don't know how comfortable you feel with special relativity from E&M, but it won't be the first time that we've seen it, at least.
I got a couple books on special relativity out of the library, and I was reading them a little bit. So, I mean, I could probably jump into it.
Yeah, so I guess maybe let's just try to get through chapter 4, and if something comes up, like, we can just do a little bit more in chapter 3 or just skip the day or something. Because at least for chapter 3 problems, I mean, I guess we could theoretically go back to chapter 2, but for chapter 3, the only really interesting, or the only one that's sort of interesting is number 4, but that's just kind of going through the motions. I feel like it's not, I don't think it's very important, since we've done the same calculation in E&M context.
Yeah, isn't it? It's totally correlated with the same potential, but the electric potential, right? Yeah.
Yeah.
I mean, I think you can use box 3.1 or whatever, table 3.1. Yeah.
Okay, so yeah, maybe the plan is let's try to get through chapter 4 by next Saturday, and if we want to just take the Saturday off instead and we can't get through it, then I think that's no big loss. But I feel like we're kind of done with chapter 3.
Take the Saturday off. I would not hear of it.
I don't know what else to do with it. Like, we could go back to chapter 2 if we really want, but
If we don't finish chapter 4 in time, we'll come on and we'll do some like mechanics problems or something.
yeah, okay, we can.
I've been working on a mechanics problem actually. I took a class when I was in college called Lagrangian dynamics.
Oh,
And when we started looking at this chapter and they were talking about Euler-Lagrange equations, I was like, I wonder if we did it in that class, because this class was in, I don't know, it was over, God, how long? Oh no, it was over 30 years ago. So it was over 30 years ago I took this class. And at the time, I didn't gain much from it. I mean, it was over my head. It really was. It was a second-year math class, and it was taught by the applied mathematics department.
mm-hmm.
But it was basically, I mean, it feels like it was a physics course. And anyway, I went back to the notes. It's like a 200-page book of notes that they printed up, and I was reading chapter 1, and they have a really interesting mechanics problem in there, where they're introducing the idea of using Euler-Lagrange equations to find the equations of motion. And I've been looking at that problem for the last couple of days. I haven't really quite worked it out yet, so I got that in my back pocket. I told Fizzbuzz I was gonna give him that problem to look at as well.
Yeah, like
I'll put it in Discord sometime, or we can look at it next weekend or something.
Yeah, sure, that'd be cool. The Euler-Lagrange equation seems like it is a really powerful thing outside of the context that we're learning about it. So
yeah,
it'd be cool to see more of how it's used.
All right, Don, I took up too much of your time here.
No, thanks for being here.
Yeah, no, it was fun.
So I'll talk to you next week.
So, yep, see you next week.
All right, see you.
Yep, thanks, bye.
Okay. Another reading group. Done. Let's switch back into normal math. Let me get some music going, and we need a minute to switch over title and category and stuff. I'll read what you wrote in a second. Underscore. We'll do that playlist. Why not? It's one of the best non-positive experiments in the history of experimental proofs. Really? Normal maths? Answering math questions from chat and studying. I think these discussions are super fun. These reading group streams are some of my favorite streams that I do. Okay, Twitch is updated. Let's update YouTube. Ah! Oh god, what did I just do? I don't think I did anything. Thank god. Okay, YouTube's updated. I need to save an image of this. We were really pushing this Excalibur, but it's all good. So let me oops. Let's write a quick announcement in the Discord with what Felix and I just talked about here for the plan. Come on. There we go. It's for chapter 3. Since we managed to get through the most important problems, let's try to push to meet on chapter 4 next Saturday. If we can't get through it in time, we might be able, even if we can't read all the way through chapter 4, there might still be some problems we can still do, just having partially read it. We'll figure out some problems to do instead. We go back to chapter 2. Maybe do things from chapter 4. Maybe look for something from chapter 4 we can't do. It has a lot of problems. Oh, good. I didn't even check that. Look for something in chapter 4 that only relies on earlier content early in the chapter. That's how to phrase that, right? Just regular mechanics we can throw that into. And a reading group. No stress though. Remember, there we go. Put that little reminder in there. This feels a little cringe. No stress though. We can't read chapter 4 in time. It's not a big deal. There we go. It always feels a little bit weird being like too positive. It's just, it starts to feel a little bit fake. I don't know if I'm overthinking it, but okay, let's send that. It's a big Excalibur. Lonely Reaper. Feel free to ask it. It's a good time. Leave that. Keep Wolfram Alpha up. It's kind of cool that we were able. In number 1, I think it's kind of cool that we literally could get that spiral graph out of it. The functional approach is very powerful, and you can reformulate pretty much any PD from physics as an optimization problem. Yeah, it feels like there's a bunch of math that we're just kind of blazing by in what we learned about in chapter 3. Of course, they don't have time to get into all of it. Because, like, isn't functional... I hope that I'm not conflating two different things, but I feel like I've heard that functional analysis is kind of a common next step after real analysis. or maybe like a grad school level extension of real analysis or something. And I assume it's the same type of functional that we're talking about. Imagine not having enough problems in life to reach for new ones in books. So it's a rare treat to not have enough problems. Okay, Lonely Reaper. Can I give a to-the-point explanation of Maclaurin series and their application? I get confused. Yes, I can. So let me start you off with Paul's online notes. I love this site for giving quick and to-the-point explanations that it sounds like you're looking for. It does not give very heavy theoretical explanations, which is just something to be aware of. But if you're just trying to get introduced to something, this website is great. So, and I'm just going to link you to it. I'm going to explain your actual question too. So a Maclaurin series is it's a way of representing many different types of functions using polynomials. Not every function can be represented with Maclaurin series, but a whole bunch of the ones you'll commonly run into can be. The math term we use to say whether it can or can't be is called analytic. If a function is analytic, that means it has a Maclaurin series. I should say Taylor series and Maclaurin series they're not quite the same thing, but they're basically interchangeable. So if I say one, just know that what I'm saying applies to the other one also. And so being able to represent a bunch of functions as polynomials is an incredibly powerful thing, because polynomials have really nice, well-known properties, and they're easy to deal with. A lot of times in like physics or engineering, you get these crazy-looking functions that are just impossible to deal with, but you can always find their power series and get a polynomial and do something with that. And so you'll very frequently see these used in approximations. That's one of their biggest strengths. So a pretty a Maclaurin series that's very good to know is the series for e to the x. I should have said, oops, sorry, I think my mic. I should have said that integration by guessing, hey, sorry, I should catch up with chat. Pretty much invented to study, was pretty much invented to study functionals like that. Biggest circle motivation was proving the Dirichlet principle. Okay. Functional approach requires good assumption of the functions you solve for to have existence and or uniqueness for the solution. You can do the physical way and assume everything works fine. Yeah. Welcome in integration by guessing. Okay. So a thing that I should have said earlier about Maclaurin series is that these polynomials are rarely finite. In fact, they're almost never finite. You have to let them go off to infinity if you want to be exactly equal. Where they use an estimation is you just kind of cut it off after a few terms. Normally, you don't need that many terms to have a pretty good approximation around an area or around a point. So I'm going to start. So if you remember who you are, I've definitely seen your name around. I don't remember if that's an alt account. I definitely have seen your name around though. And so I just need to remember it is. No, I remember the power series off the top of my head. Okay, let me actually just show it to you though. Okay. I'll drop the link to this in the YouTube chat. So the power series for e to the x looks like this, or if you want to, you can compact it into summation notation. And it's kind of amazing that this exponential function, you can make it just a regular polynomial. It goes off to infinity, but these things are equal to each other. I mean, that sentence might need a pure mathematician might take issue with the word equals, but for the sake of what we're doing here, these things are exactly equal. Or there might be some like nuance there that I'm glazing over. We don't have to worry about it. And the cool thing to do here is let's just build up the series for e just by looking at one term. Like we'll start by looking at just one, and then we'll put in the plus x, and we'll like keep on adding one more term and seeing how it evolves. A doubt in complex numbers? I can try it. It's not my strength, but if you only can give me the problem, I'll try. Okay, so the first term in the power series is just 1. It probably wants me to do y equals that. All right, and so when we're looking at a Taylor series, we always, or a Maclaurin series, a Maclaurin series is always approximating a function around 0, specifically. That's what it means to be a Maclaurin series. A Taylor series can approximate around any point you want. Maclaurin series is always 0. That's the only difference. And so our first term is just 1. Around 0, this is a pretty crappy approximation. I wouldn't use this for much. It's exactly equal right at 0, but as soon as you get a little bit left or a little bit right, we're getting pretty far off. And so let's add in the next term, which is just x. Representation-based problem? You can put it in my Discord. It's the easiest thing. So we know this is called a first order approximation. This is first order, right? I'm pretty sure that you would call this first order because it goes to the first derivative. Hey, Abrar. And so you can see around 0 here, we're actually kind of talking now. Like, there's a little like square here where these functions are nearly the same. Yeah, Jed, I think that'd be the 0th order. I was getting a little bit mixed up on those. And so these lines are really close to each other already around here. And so now let's add in one more term. The next one is x squared over 2. And this is even better still. Like, the square where this is a good approximation just got a little bit bigger. Like, these things are basically on top of each other for a pretty long time. Like, between, you know, what do you call it? Like, minus 0.2 and plus 0.2 or so. And the point is, if we keep on adding these terms on, it only gets better and better and better. Like the window where the thing's a good approximation only gets bigger. Graph them all independently? We could. I don't know if it'd be that helpful though. Or I don't think it's going to show us what we want to show. I'm not sure, but maybe you have a point there, Jed. I just don't know what to do with it. And so now if I get a little bit fancier, and I go to this, I want to be able to this thing. If we have a bunch of terms, let's just say we have 100 terms, and I'm going to put in the generic definition here and factorial. Am I slowing down Desmos? Nope. Okay. Let's get rid of the blue. Oh yeah, see? So sorry, I should if I make this upper bound here 3, it's the exact same function that we have here. Actually, let me make this A. So, sorry, I maybe shouldn't mess around with this more than I am, but I'm going to do it. Okay, so here, if I make A3, we're going out to the third term or to the third order term, which is that one there. So this is the same thing we're just looking at. And so if I keep on increasing this, 4, even better, 5, 6, like it's the more terms you include, the closer it becomes to the actual e to the x function. And so if I suddenly bump it up to 100, like, it looks really good. If I went far enough to the left or right, it would eventually start looking bad. Yeah, see, like over here, it gets crazy. Like, who knows what's happening over here? But the point is that the more terms you have, the more exact you get. And if you go off literally to infinity, it becomes a perfect approximation everywhere. Now, e to the x is a nice example. There are other functions where even with infinitely many terms, it's not perfect everywhere. It's only perfect in certain parts of the function. E to the x is just an especially nice example. So there is a certain radius of convergence that these things have. That's the idea that I'm referring to. So like on this sheet here, x can be any real number. But if we look at this one up here, this series only converges when x is between -1 and 1. So I think that's an interesting example to look at. So 1 over 1 minus x, that's the function that we're interested in. The series from n equals, it should be 0, right? Yeah. And I'll make it to a, the same thing. And that's just x to the n. See, and so this series, it's even with a bunch of terms, or infinitely many terms, it's only a good approximation between -1 and 1. That's just an unfortunate consequence of how the function looks. There is a separate, you could get a second power series that perfectly approximates the other part of this graph, actually. Syntax, yeah, sure. The limitation of Desmos, not the actual graph. Oh, yeah, it's possible that Desmos is just messing things up too. So yeah, I guess the moral of the story is that a Maclaurin series gives a way to approximate functions, and if you let them go to infinity, it's a perfect match. The only caveat being that it may not be a perfect match for every possible value of x. Sometimes it is, sometimes it isn't. Click on the play button? Yeah, sure. So who asked that question originally? That was Lonely Reaper? Okay, yeah. So Lonely Reaper, I think it's everything that I have to say offhand. If you want to hear about anything in particular, or you have a question about what I said, please do let me know. Otherwise, I'm going to move on. Derive the power series for arctan from the geometric series, right? I believe that process is you would take this series, plug in, I guess, -x squared and integrate it. Yeah, that's what it looks like. Why does that power series converge for x equals 1 as well, even though the geometry? So you're asking, this one is a closed interval, and this one is an open interval, and that's what your question's about. Counterexample, e to the minus 1 over x squared. Oh, for like a non-analytic function. Says use 0, okay. Syntax error. The quick answer is that the series for arctan is saved. The denominator saves it for arctan, I think. Because this is still basically a geometric series, I think. But being divided by 2 or nearly by 2, I think makes it a bit more generous for where it converges, as well as being alternating. Well, maybe not the alternating piece. Let's go through it and try to harmonics diverge. I mean, let's go through it and actually try this. Oh wait, did the other person ask their question? Okay, no, I don't see them having posted their question. So someone said they have a complex variables question, but I don't see it posted anywhere. Welcome back, Lucas. So yeah, let's actually try. Let's do the ratio test here. Oh yeah, that's a way of approximating pi. Have you ever done Taylor series for multivariable functions? My course only showed up until order 2. You can see how crazy you'd be to go beyond that. There's a lot of partials. Ooh. I might have seen it somewhere. I never had a course that goes over that, though. I can imagine that would get extremely crazy, though. I'm a Ruski Kot Don? I don't know what that means. Welcome back, Jasu. Hope your thesis writing was going well. Oh, a Russian cat? Okay. Okay, I see your question, Adarsh. I'm gonna talk about syntax errors question, and then you'll be next. 200 words? Hey, that's something. I'm just gonna take that series there. We want to test the endpoints. I guess I should say, I think because we're taking this power series from x to the n, and that converges over -1 to 1, I think any series we derive from this is going to have the same endpoints, but we have to retest if they're included or excluded. I think that's a fact. I don't quite remember that for sure. But if we do retest these endpoints, let's check x equals -1 first. I'm having a hard time saying why. It just feels right to me. I feel like I learned that at some point, but I can't remember the justification. Lucas, this is... I might have explained it while you were here before, but this is like a Maclaurin series, which can be used for approximating functions. Sorry, Adarsh, I think your question is going to take some time to answer even once I start on it. And this question is going to be shorter. Okay, so I'm just going to get rid of the negative ones. We don't care about that. -1 to the 2 n plus 1 minus 1. 2n plus 1 minus 1 over -1 to the 2n minus 1 over 2n minus 1. There's probably a stack exchange thread that'll explain why the endpoints stay the same. I'm gonna... We can look into that after we check this. So these negative ones go away also, because of the absolute value. So we really just end up with 2n plus 1 minus 1. No, we don't. 2n minus 1 over 2n plus 1. Well, that's not good. Replacement Lucas means that each time you take a ball out, you check if it's right, and then you put it back in. Yeah, this does suck. How do we deal with this? You're right. Alternating series test is much better. How does positive? Oh no. Positive don't have the same justification. Um. This is just equal to -1, that piece. The series is going to simplify to -1 to the n, 1 over 2n minus 1. Okay, and then yeah, we can say this thing converges by alternating series test. The limit goes to 0. And just for the sake of time, for x equals +1, it's still alternating. So the exact same test will apply. And so yeah, so the alternation definitely helps save the endpoints then. And we don't have alternation in the geometric series. The geometric power series. Is there a good explanation for why the endpoints don't change? Does the interval of convergence change for the derivative of a power series? Ooh, is this the exact same question? Yeah, this is the exact same question. Many geniuses ponder these. Among them use syntax. I wouldn't really call this an answer. They're stating the result, but not why. I'm sure that has a name, right? The radius is the same after taking the derivative or integrating, but the interval may change. I don't like any of these answers. Like, this has to be a theorem somewhere, right? Like, I want to find the name of this idea. Hmm. Oh, that's a new one. Not the questions that are hard, it's the answers. Cauchy test, yeah. I don't know. This is kind of unsatisfying. I want to know why. One second, I just got a text. Okay. Um, what, like, presumably the idea that a power series, the radius of convergence of a power series does not change with differentiation and integration has a name. Or, like, surely someone has named that result after themselves, and I'm just trying to figure out what the name of that is. Like, there's no way some mathematician hasn't wanted to stick their last name on that. Never saw a name attached to it. That's kind of amazing. Abel's theorem? Let's Google it. Or at least, like, does that property, like, just have a name in general, I guess? Yeah, Adarsh, you'll be next. I just like to. It's kind of annoying. Like So okay, this question came from syntax error, basically asking the geometric power series. This thing converges on the open interval -1 to 1. You can do some substitutions and integration to find the power series for arctan. Why does arctan converge over the closed interval -1 to 1? The unsatisfying answer, in my opinion, is that you go and recheck the endpoints and just find that it does. I was hoping for a higher level answer, I guess. I can't really find it, though. And also, like, why would it have to be that any series you derive from this should have the same radius? Like, why? Anders, please crappily draw yourself, crappily drawing the previous crappy drawing that was redeemed. Okay, we do have a complex variables question we're gonna have to answer first. And I guess a question from Lucas. But I can work on it then. I hope you're doing well, Anders. It's always great to hear from you. If you want a complex analysis explanation, if an analytic function is defined of some open distance, then so is its derivative. So both the Taylor series must converge. I guess so. I don't know. Maybe it's not as deep as I think. Maybe I'm reading too much into it. So yeah, I guess it would never make sense for something derived from this series to have a bigger radius. Because this series is only valid in the first place over a certain interval. So you're never going to do something with that. And oh, I'm so sorry, Kikado Akian. Hi. I read your chat and I forgot to actually say hi because I was so distracted in thinking about it. But hello, welcome in. I'm sorry I missed your chat. So yeah, it wouldn't make sense to have a bigger radius because that just seems like a non-starter. I guess I don't see why it would get smaller. Okay, yeah. Think about it with the ratio test. Write down the power series, then differentiate it. Apply the ratio test to both and compare. Oh yeah, underscore. I guess I see what you're saying. Like we can even just do it with a simpler one, like the like just the geometric one, just to keep things simple, right? The derivative of that bad boy. What is? Oh my god, this sigma is terrible. N equals 1 to infinity, n x to the n minus 1. Yeah, if you were to do the ratio test on each of these, the ratio test is going to always work out to be the exact same, right? Or is it? We're taking x equal 1. Nope, this is no. This is 1. What am I talking about? This is n plus 1 times 1 to the n over n times 1 to the n minus 1. There we go. Okay, and so the lesson here is that if you take the derivative and apply the ratio test, with how the power rule works, you're not doing much, I guess? Is that what you're getting at, underscore? But it does change in other situations. It changed in this. I guess the ratio test doesn't change. That's why oh no, I shouldn't have done it at an endpoint. I should have done it in general. That's the thing. Let me catch up with chat. We take derivatives to make the coefficients bigger. On the interior, the ratio test still works. When a two continuous function uniformly converges on a set, it also converges on the closure of the set. Hey, skeleton. Oh, interesting. Okay. Just use your reference of examples. Cauchy-Hadamard theorem. I'll take a look at that in a second. I just want to. I think now I understand what the point the underscore is trying to make, which is if you're finding the interval of the radius of convergence, and doing that less than 1, this limit is going to be fundamentally the same thing as the limit of the derivative too. Like, taking a derivative of this thing isn't going to change much. When I say of this thing, it's more like of this thing, or sorry, of this thing, then applying the ratio test. Like, I don't mean like use the quotient rule. N plus 1 x to the n over n x to the n minus 1. These two things are basically the same limit, because this chunk here, this limit is just 1 as n goes to infinity. And this limit is basically the same as that. So, okay, that's the point. Let me look up Cauchy-Hadamard, and then we're going to look at... Oh, no! Ah, it got all stretchy. You can see the important part, though. I hate it when it gets stretchy. Okay. Cauchy-Hadamard theorem. Wasn't keeping an eye on the stretchiness? No worries. Sigma sign is terribly needed. It is really annoying to draw. Okay, so yeah, Sakachin started talking about this. So yes, Index, if you want to really dive into this, I guess this is the thing that you would want. I feel a little bit too stupid right now to try to dive into this and really understand it right now. But I do like underscores more casual or like informal suggestion of just looking at for a proof of why the radius of convergence is the same, an informal proof, this demonstration with the ratio test I think is sufficient. And you can't, and like the ratio test not working at the endpoints is the exact reason why you need to check the endpoints separately after doing a derivative. For like 50 intervals the other day, your intervals started looking like sigmas. Oh no. Radius doesn't change. It's derivative, intuition, the ratio test, true proof via Cauchy-Hadamard, which is the root test. Order can change. Yeah. 10 analysis secrets around this. Yeah, I mean, I think the explanation that's on the screen right now is a nice demonstration of it, even if not a proof. But the actual proof probably involves some contortions. Okay, Adarsh has been patiently waiting. Thank you for that, Adarsh. Let's look at this question. I'm bringing it up momentarily. Jed, thank you for confirming which one it is off that sheet. And Lucas, you'll be on deck for after this. The Discord or the YouTube works. As high school student, you can't get a shit what's going on in here. It just looks satisfying. You're doing this in high school. Okay. The value, actually, wait, I'm not, I just reduced, I'm missing some context. I shouldn't have done this exactly. Z1, Z2, Z3 aren't generic. There you go. There's some question in the middle that I was trying to cut out. So Darsh is only asking about this one. Should I just get the entire image? I feel like I should just get the entire image now. I don't think we'll need the first two, but just in case. So, they're only asking about the third one here. The first two they're fine on. I'll keep the first two up here in case they're relevant in some way. I don't like having challenges. I want easy questions. Topology? I can't do topology. I just see that in the thumbnail. I can look at it, but I'm probably not going to be able to solve anything. It'll be after this. Oh, nice. Maclaurin recommended skeleton and book. It's awesome. It's a video that Lucas posted in the Discord. I think it's just going to be for fun. Okay, in the Arctan plane with Z1, Z2, Z3 are respectively the vertices of an isosceles triangle ABC with AC equals BC and CAB equals theta. In center. I gotta remember what in center is. Oh no. Can we place these strategically? Like, I want to make my isosceles triangle, I guess, like this. And what vertices need to go where? AC equals BC. So C is at the top. Hey, MTK, thanks for the kind words. CAB is theta. Presumably Z1 is A, Z2 is B, Z is Z, C is Z3. What the hell is in center? Oh wait, oh Jed, you said it. The center of the circle inscribed inside the triangle that is tangent to all three sides, also the intersection of the angle bisectors. Isn't that just terrible? You hate to see it. I assume the bisector thing is going to be more helpful here. CAB instead of BAC. I don't know, Jasper. That's a good point, though. Okay, and so what's question 6 here? The value of Z2 minus Z1 squared tan theta over 2. So is the question really to get tan theta and tan theta over 2 in terms of z1, z2, z3 in z4? So I think we can cut this triangle in half maybe. Just look at that part of the triangle. Connect Z4 to B, which has the same angle. Yeah. So I don't know if I'm misleading myself with how I've drawn this. Let me label my angles first. But is tan theta simply opposite Z3 over adjacent Z1? I'm a little bit concerned we have to do some offsets. Like, I kind of centered this triangle in a nice way. But the same idea, tan theta over 2 would just be Z4 over Z1. And given expression is equal to 4 times the height of the triangle. Oh, Anders, if you are still here, the drawing is going to be in Excalibur, or at, like, in Journal++. I hope that's okay with you. If not, tell me, and I'll refund you. I still have the whiteboard, but I don't want to use it. I don't have it set up. You think the given expression is equal to 4 times the height of the triangle times the radius. Like, the drawing is just going to be in this program here. Like, I'm just going to do it on a blank page. Like, this is what I'll draw on. If you're not okay with that, that's okay, but just, like, let me know. The last digit of 23 to the 23 to the 23. I'm not doing that right now. This can't be right, right? This is too simple. And like, why do none of these have division? Am I, like, what am I missing here? The given expression is equal to 4 times the height of the triangle times the radius of the inscribed circle. So I was putting the origin. I mean, I thought like this up here would be a convenient choice of things, but I don't know if that's general. Um, Oh, wait, I see in question 4, AB is Z2 minus Z1. So I should back up. I think what I'm doing isn't right. I think tan theta is equal to AB over 2 over whatever the height is. But AB, I think, is Z2 minus Z1. A gives us the answer you came up with. If I put the origin where you did, but we should check signs. I think my answer couldn't have been right. My answer would have involved fractions, and there are no fractions in the answer. How do I express the height of this isosceles triangle? I'm getting confused on this. I think we care about Z4 for tan theta over 2. Yeah, I still don't know how to express this side of the triangle in terms of the complex numbers. AB, I think we can just say Z2 minus Z1. I don't know what the other piece is supposed to be, though. My placement of origin was key. I might able to just put the origin there. It'd be nice. I didn't know if that's allowed or not. Oh, also, I have this flipped, don't I? This is adjacent. The height of the triangle is Z3. The radius of the in circle. Alright, I'm just gonna trust this then. Or trust this and trust you. Isn't Z4 the height of the smaller isosceles triangle? Why would it be the radius of the incenter? C4 is the center of the inscribed circle. But with my choice of origin, it's just on the imaginary axis. I don't think it's a radius, I think it's the center. Wait, yeah. If Z4 is the center of the inscribed circle, then how is the radius of the incircle Z4? Oh, duh! With my choice of origin, yeah. Okay, sure. Aren't they getting something that looks too simple, though? I'm getting 4 Z3 Z4. So you would say the answer is none? Like D from books? You think it's A? Oh, you're saying... Oh. The Z1 plus... That's so stupid. I hate that. But you're right. With my choice of origin, it would be 0. Oh my god. Okay. I guess, yeah. Adarsh, are you still here? Wait, we think the answer is A. You are? Okay. So, at least with the origin that I took, putting it at the base of the isosceles triangle, you can show that tangent theta is equal to the height of the isosceles triangle over half the base. And so I get Z3 over Z2 minus Z1 over 2. Tangent theta over 2 is the height of the smaller triangle that goes up to the incenter over the same half base. So Z4 over Z2 minus Z1 over 2. And then when you plug in to this form here, the tan theta becomes that, 2Z3 over Z2 minus Z1. The tan theta over 2 equals this, 2Z4 over Z2 minus Z1. And it simplifies down to 4Z3 Z4. Now, that doesn't match any of the answers given because for the choice of origin that I made, Z1 plus Z2 is 0. Like, looking back at the diagram, B is a real positive number. A is the negative version of that real number. So you just have to realize that for the choice of origin that I made here, I guess, that I missed out on that bit of information, I guess. If I was doing this blind, I don't know I would have gotten that. But yeah, Complex variables are not my strong suit, so I'm not explaining this as well as I possibly could. But I think that's basically the answer there. What year am I in, Lucas? I graduated with a bachelor's a long time ago, if you mean me. Okay. The person who asked this question, I wouldn't worry about it. Adarsh said that they're in high school. But I've been there in a very like different countries structure their math completely differently. I wouldn't compare yourself to someone from like I wouldn't compare yourself to someone who like you shouldn't. I learned basically no complex variables when I was in high school. Hey, Shoria. Like I learned that the imaginary number exists, and I think that was the entirety of complex variables that I learned in high school. They also just get insane. Some people in some countries just get insane questions that I can't even solve with all the math knowledge that I have currently. I would not, if you can't solve that, do not worry about it. You like your numbers like you like your friends imaginary? See how it's like, Jess, we did have solve stuff like this, but this is way harder than a lot of people have to ever do. Well, I mean, I don't know if it's like, this isn't like crazy hard, but I wouldn't read too much into it. Hey, Papadoria. Okay, Lucas, it's just a YouTube short, so I'll quickly look through it. I don't think I'm going to answer any of them, though. So I'm probably not. I might try and, like, verbally talk through it, but I don't really like watching videos on stream to the extent I can help it. Okay, yeah, dumb. I can do that. Watching videos means you don't have to produce actual content. That's a strong point, Megalomorph. I can just react to this. Adarsh, yeah, I think so. Two real numbers x less than y should exist in S. That's irrational, which is between those two numbers. Ooh. I probably couldn't do that offhand. I am sure I can understand a proof of that. If you locked me in a room with a piece of paper and told me to solve it, though, I don't know that I could. Proof of rational, more aesthetic in European Mert? Fair enough. Abstract algebra is a whole 4. Oh, I've hardly studied rings. Proven isomorphism? I don't know how to do that. This looks like a bug in this thumbnail. Like a little larva. Sorry. Level 5 is topology. I have no fucking clue. I have heard of JE Advanced. I hate those questions, and I think they're dumb, to be honest. I don't think they test real math skill. The ring stuff you didn't take your undergrad? Yeah, I probably would too if I did the pure math route. Slightly NSF. Yeah, I don't care. I don't have family friendly stream. How does a math joke? We're about to find out. apparently. Okay, Anders redeemed the drawing. Oh, Buddha did, sorry, Skeleton did a quick math. But I don't know that I can do that, and it breaks the rules of quick math. Taking topology in 6 months, so hopefully it goes good. Ooh, yeah, good luck. I can do that quick math. Speaking of workout problems, how does the mathematician work out the problem of constipation? Like every problem with the paper and pencil? Oh god. I think I'll just live with being constipated if that's my option. Benlux is giving me encouragement? How dare? 23 to the 23. I assume to the 23 like that, like a power tower. Yeah, I mean, that is very slight NSFW. Oh, is that just 3 times 23? Is that all we care about? And that ends in 9? And then this will end in 7? Question mark? Wait, no, 923 times? Yeah. Okay, I'm saying 7, I guess. I read that at math camp like 25 years ago. No? No. That's what you get for believing me, Fenbox. I clearly can't do it. 23 to the 23. That's 23 times. No, that... No, 3 to the 23? That's what I should be thinking about? No worries, Adarsh. Check for mod 10, then check for mod 4 for 23 to the 23. We can just take 3971 on mod 10. Periodicity of 4. Did you hear about the group theorist who thought he discovered a new simple group? He flushed it down the toilet when he found out it was P-soluble. Oh my god. That's a very nerdy joke. What does the p-adic norm measure? Penis? Oh. That's some deeply nerdy math jokes. So yeah, okay, if you repeatedly multiply 3, you get 3, like 3 to the 1 goes to 3. 3 to the 2 goes to 9. 3 to the 3 goes to 1. 3 to the 4 goes back to 3. That's the periodicity of 4 that Mert is trying to put me onto. And so presumably wrong? Oh, yeah, duh. 7. That's 1. There we go. Yeah, thank you, Mert. And Jed. So then 23 to the 23 presumably is going to end in 7? Is that what I said before? I don't remember. Because this is 1 less than a multiple of 4. I said 9 before? Okay. Rin, I feel like you're just quizzing me with that, and I'm not really interested. So now we have to worry about powers of 7, I guess? 3 to the 5 goes to 3? Yeah, it would. The 2 goes to 9. 7 cubed is going to go to 3? 7 to the 4 go to 1. And now we're repeating. So this is 1 less than a power of 4 again. So it's going to end in 3? Wait, did I mess up before? We don't need to do 7? Why not? Ren, if you're gonna find a question to ask me, please don't. I want to do questions people need help with. I think you're just trying to test me. I'm not interested. Um. I mean, okay, then the thing I'm strongest on is probably just like regular like first and second year calculus. That's like my comfort zone. Oh, sorry, like first and second semester calculus. You checked it for mod 10 last digit. It is for something watching Twitch. Um, is the answer just 3? So Lucas, the question was, it wasn't to actually do this. The question was, what is the last digit? Of this number. And the trick that we're using is that if you do 23 times 23, just do it the old-fashioned way. That's 9, 69, 0. The 0 here is the important bit. Oh, come on. It doesn't... Wait, did I even do that right? Yeah, okay, I did. Like, this last digit here is just going to be 3 times 3 is 9. And so that's why I'm only worrying about powers of 3 here, because if we keep on multiplying by 23, we only care about the last digit. Only round to the nearest 10th? I like that technique, Jed. Wait, did you watch Megalomorph stream back in, like, I assume that, like, Megalomorph hasn't streamed in forever, right? Did you, like, are you that much of an OG Fenbox that you watched a Mega stream? Or did Mega stream recently and I just missed it? It's been a few years. Okay, yeah. Man, I'm missing out then. I wish I saw a Mega stream. Ends in a 7. I said 3. Well, that sucks. Merc guessed 7. Alright, I'm refunding Skeleton's points. Yeah, sure, Glorioso Tom. Like, poop, pee, penis, vagina, boobs, shit, fuck, sex. I don't know. I, hmm. I don't like that we don't do the last part, Mert. I know that you explained it, but I just don't, I don't know why. Or I don't understand it, I guess. We can just take 3971 on mod 10. I don't know. We checked it for mod 10 last digit. I'm not good enough with the stuff to understand why. Fellow mathematician is having trouble with his wife. It's going to be a divorce. The story is that he's nilpotent and hasn't funked her in ages. Oh, that's a good one, Tom. Johnny Bat, you don't need an 18 plus tag on Twitch. Twitch already has a mandatory like minimum age. There's like tags that you can theoretically put on your stream for language or something, but I think you have to be really out there. It's the volume of a whole deep dish pizza with height A and radius Z. I think you would use the volume of a cylinder, right? Yeah, like if you ever like look in a category on Twitch and certain streams are like blurred out, it said like may contain like sexual themes or something. Streamers can put that on for themselves. But I've never done that. I don't think I have. Show you a whole deep dish pizza? I wish I had one to show you. I can show it. Or you probably mean the volume of a cylinder. Pie. Oh, pizza! Pi z squared a, and it spells out pizza. That's funny. You thought that was for swearing? I think there is one for swearing, but you can. I don't think you need to put. I don't know when you will put on your stream, but like, I don't know. Fuck, shit, damn, bastard, bitch. All those good words. Lucas, the reason I was looking at 23 times 23 is because for higher powers of 23, you're basically repeating the process. Like for 23 cubed, it will be some number that ends in 9 times 23, and you do the exact same exercise and end up with a 7. Talk like a sailor? Yeah. Find its possible values for 10. I still don't understand that, Mer. I'm sorry. It's me being dumb. In the like, well, yeah. So I was kind of like, that's another way I was just finding it in my head. Oh no. Yes. Oh, okay. So once we figured out what 3 to the 23 is, well, that's a number that ends in 7. I don't get it, Silmer. I'm sorry. Okay, I want to do Anders' drawing. Please crappily draw yourself. Crappily crappily draw myself crappily drawing the previous crappy drawing that was redeemed. The previous drawing that was redeemed. Let me find it. Was from Mean Machine Rex. Mia's Hollow Knight. Happily, yeah. I don't know where the 100 was coming from in that Mert. We're right at 29. 100, or I don't know why it's 129. It's okay. Like it's hard for me to understand things when I'm streaming because I don't really get to focus on one thing at a time. I just don't think I'm going to understand it. So I have to crappily draw myself crappily drawing this. Distinction between fuck and shit. What do you mean distinction between fuck and shit? They're just kind of two different words. Or I mean, one is a noun, the other is a verb. That's true. Physicist, biologist, mathematician are sitting on a bench across from a house. They watch as two people go into the house, then a little later, three people walk out. Physicist says the initial measurement is incorrect. The biologist says they must have reproduced. Mathematician says if exactly 1% enters that house, it will be empty. Oh. Because there's like a negative person in there. In the guidelines? I don't know for what guidelines. Okay. I guess I need to, so I'm drawing this just like on my tablet. So I guess I need to draw me at my tablet. Let's start with a chair. Draw it a little bigger. How do legs work? I guess I have legs like that. Please don't make fun of my one of my legs is longer than the other. Please don't make fun of me. I'm very sensitive about it. Well, let's take another whack at it. I don't know if that's better. Okay, now we need a desk. I need to draw it closer. The ergonomics of this are all sorts of off. You actually, I mean, I think that's actually a thing. Like pretty much every human has one leg longer than the other. I'm just making a dumb joke about my lack of ability to draw. But I think human beings generally aren't very symmetric if you really measure things well. Quarter-inch long. Wow, that feels kind of significant. I think, no. I remember in a biology class, we measured like wingspan to height and did that as a ratio. I don't think we measured like length of each leg though. Your uncle was so badly longer than that they did surgery by cutting and there were bolts coming out? What the hell? That's kind of crazy. A mathematician is cooking with a pan on a stove and suddenly the oil bursts into flames. The flames roar and the house starts to fill with smoke. He runs into a closet, strikes a match, then blows it out again, breathes a sigh of relief and says, "Phew, a solution exists." Oh my god. Now draw me looking at you drawing yourself, drawing the previous crappy drawing that you drew. You had made custom riding boots, so they measured the length of your calf. Like for riding horses? Oh no. I scrolled up. Wait, how does my hair look? I guess it's parted like that. My hair is not very symmetric either. Okay, and now we need to get the Hollow Knight. Let's get the mouse on the desk too. For horse riding, that's kind of sick. Okay, so then the previous drawing was me as Hollow Knight. So I guess we'll start with the blue cape. That looks bad. Zoom and enhance. I'm working on the details. Everyone's a critic. Forgot it was a pad, yeah. I may have made this too small. Okay, you know what? Just for you, Anders, I'm gonna erase it and make it a little bit bigger. It is supposed to be a crappy drawing, that's true. I should have just done like, there, crappy drawing, done. I'm just gonna have a big old monitor. I'm sure this is great for my eyes. It's not quite symmetric with the stand now either. You know, that's just an issue of the perspective, though. That's how I'm gonna explain that. Right, the perspective. Mm-hmm. Ah. Have some Squidward-like legs. That's just how I sit at my computer, okay? Completely naked. Just as dot very zoomed out. Hey, Tree, I'm back. What? Do you actually wear clothes when you're at your computer? Come on. Be honest. Ah, it's not good. It's better. Okay, I think we can fill in some here. Why wear clothes at home? It's just extra laundry. See, and that's more sustainable too, because you're not using as much water on washing your clothes or energy. This is really a great sustainability initiative. Just become a nudist. I did draw myself with an AK-47 on my back, so we better get that in there. What's my screen time? It's way too much. I'd rather not think about it. I forgot to draw the rest of my chair. Get little wheels on it. You thought it was a math stream? Oh, well, you thought wrong, color code. The math thing is just a bait. Really, this is a nudist art stream. Forgot my armrest. Some of us don't live in a strip club. Well, I'm glad I'm not. I'm glad I'm not in that group of people. All right, how's that, Anders? What's my life like? Right now it's mostly just streaming. It's not much to tell. Come for the math, stay for the nudist art. Mm-hmm. But also, if you did live in a strip club, you would probably be super buff because pole dancing is such a good workout. Yeah. Oh yeah, you're right. You guys can see that I am wearing something up above here. But for all you know, I am just like Winnie the Pooh. What's shirt cocking? Do I have any hobbies? My biggest one is coffee. Just like brewing good coffee. Go to an art gallery shirt's worth $1 million. Thank you, thank you. How do I make a t-shirt? Also, I appreciate the caution, but I don't care if you guys want to just say stripping. This is kind of terrible. Ta-da! There we go, shirt. Oh, string theory. I get the joke that you're making, $10. And addiction, not a hobby. That's like answering wine to a hobby. I mean, people would say they have wine as a hobby. On tea, I don't mind tea. I would love to try like actually good loose leaf tea. I never have though. I'd love to go to like a tea shop and try it. I've only ever gotten like cheap tea bags from the grocery store. I do drink herbal tea pretty much every day because I would lose my voice if I didn't. Am I married? No. Great. I'm glad you're another satisfied customer. Matthew Juan, I'm probably saying that wrong. But yeah, I sure try to. If you have a question, feel free to let me know. You can put it there in chat, or you can put it in my Discord. He's a sacred thing for us, Mert says. Oh, cool. Like, what do you, like, is that a, like, literally like a spiritual thing? Like, for like religious ceremonies? Do I love Magnus Carlsen? I wouldn't say I love him. He's a fantastic chess player, and he plays some really good chess. I wouldn't say love, though. I don't hate him, though, either. I'm putting this in the Discord right now. Main drink for every breakfast. Turkish people consume so much tea. Really? I've heard of Turkish coffee, and I'm very interested to try that. I didn't know that Turkish people were big on tea, though. 100 out of 23 to the 23 to the 23. Oh, so it's a really crappy score. You know, that's good, though. That was the task. Barely 5 cups of tea per day. That's a lot of tea. People say Magnus has more IQ than Einstein. I think IQ is at best limited in what it measures, but I have they both taken IQ tests? Fame has yet to find you a gay billionaire husband that lives on the other side of the world. Are you really asking for too much? You know, that's really mean of your family, Jasu. I can't believe it. You should look for a new family. Matthew asks, take a morphism f from SLNC. I already can't do this question. From 2SLDC, which is a polynomial. And the coefficient of f of m is polynomial in the coefficient of m. Show that f respects unipotent decomposition m equals d, where d is diagonalizable and u is unipotent, and they commute. That is well beyond me. I hope someone in chat would know how to do it. But yeah, my background is I have a bachelor's in applied math, and I kind of avoided any sort of abstract class, and this seems like a I don't know what you would call it, but it's the type of math that I haven't learned. Coffee is more popular and cultural for us, but tea is in our life and barely everywhere. Oh, that's cool to hear, Mert. Here, yeah, I mean, I was looking for a more specific term, like abstract algebra or linear algebra or something. I was asked this at my entrance exam at ENSULM. Still don't know precisely how to do it. I don't know even vaguely how to do it, much less precisely. I don't even know who I could like. Who might know about that? Like maybe Academy of Useless Ideas might know about it. I'm not really sure though. Hmm. I don't know what ENSULM is, but I assume that's like graduate level or something. I would hope that's not like a university entrance exam question. You understand the question? You just haven't done any decomposition in ages? Okay. École Normale Supérieure. French University? Oh, okay. Yeah, so it's not where Galois try to get into. I don't know. Um, so yeah, I'm sorry, Matthew, but I'm not gonna know how to do it. Someone else in chat may know, or just be able to give a hint or something. So I do see that you're a new person around here. Whenever I do see new people, I do like to let them know that the math niche exists on Twitch. So that there's a whole list of people who do math help streams of some kind. I don't know that any of them in particular would know how to do your question there. The person who isn't on that list is Academy of Useless Ideas. It's possible he would know about it. I can't really promise that though. I don't really know um the areas of math that he's good at. Oh, well, thanks so much. Yes, Stuki may. That's true. I'm not sure when they're going to stream next, but it's possible that Ian Stuki would. Hmm. Yeah, I appreciate you trying and welcome in. Um. Okay, so I guess we've hit a slow bit where we don't have a question that I know how to do at least. I could look. I don't want to stream for a ton longer, but we could look for like another question or two just to work on for fun. Um. You know, since it's on my mind, I kind of want to do that. Like this should be a simple calculation from the general relativity book. I could just try to do that. It theoretically should be simple. It's probably famous last words. It's honestly, it's kind of been on my mind for the entire stream. So you're about to say that? me bring up the formula. Where is the formula? The formular. There it is. You know, I had screenshots saved already. Oh well, it doesn't matter. And bachelor's, more. So I have a bachelor's in applied math and a minor in computer science. It's a 4-year degree. I'm starting on a master's in the fall. But yeah, that's my my background. The Newton formula. Don does coding when? I have done it before. Which one is the Newton formula? Oh, this one? So like I used to be a downtime activity on the stream that I would do like Project Euler questions. And Zach and I have had at least 2 coding competitions, maybe 3. I enjoy coding small things. I tend to lose motivation for big things because it just gets so tedious. Hey, Abhinav, hope you're doing well. Newton's theorem? And now just Maxwell's equation to compute it? Yeah, I was hoping to do it like with an integral. But that might just not be the best way. 322. Hey, Walter. Oh. Uniform mass density, radius r, total mass m. Is that not the exact thing they did here? I'm doing well. How about you, Walter? Yeah, so they kind of already did the outside case, did they not? I was going to go to the integral definition for the inside case. And I expect the inside case to be linear, because I think that's what it was for a charged sphere. Also, why does this formula look different? Wait, integrate both sides with 3.17. Oh. I forgot they did it in this weird way. You've been super unproductive, famished? Oh no. What's up? Lots of coffee. Why am I getting stupid? Take yourself breaks, but since the end of the month's come, you gotta grind. Fair enough. Their technique, I thought I had figured it out when I read it, and now that I'm rereading it, I need to remember what the hell they're doing here again. It's weird to me that they use the differential form and integrate it when they already have an integrated form. I remember that for E and M, it just scales up linearly. And it's a good idea to check that like it scales up linearly, and then once you're outside, it falls off with 1 over r. And you should make sure to check that the line meets the 1 over r. Homemade chicken sandwiches for dinner? Ooh, that sounds great. I'm just trying to figure out how to like arrive there. I'm basically trying to steal this work here. So if we have, looking at this one on the right side, this volume integral, hey Chendu, that volume integral, when it's not over the entire sphere, we need to figure out how much of the mass is contained in a smaller sphere, radius small r. Oh, and that's going to be rho divided by, no, it's going to be volume of that sphere divided by rho. I need to write this down. So let's say the density is equal to total mass over 4/3 pi r cubed. That's the volume of a sphere, I think, in hope. Linux? I don't know much about Linux myself. Yeah, maybe I... But we want it. Do you have a question about Linux though, Chandu? There might be someone around who knows. There's some known Linux enjoyers. Oh, am I using it? No. I'm on Windows. Program is strange. It's called Journal++. It's not the best, but it's good enough. Uh, I'm I'm good. This one, I'm in theory interested in writing a plugin for this at some point. I guess OneNote probably has plugins too, but this one just seemed more appealing because it's open source. Um, so what is this volume integral when it's not over the entire thing? It should result in a mass. That's what we want, right? It's going to be rho times the volume. That's my guess. And the thing on the left side, they convert to an area integral using the divergence theorem. Did exact this integral the other day. Didn't see what the integral on the right-hand side was. It's just the mass. Yeah. Symmetry of the distribution, then invariance, Curie principle. I feel like you know a lot more physics than I do. This question should be within my grasp using tools that I have. I'm just trying to figure out how to express it because it's kind of at the edge of my knowledge. I don't think I need to go to. I think I should be able to do this problem without something that. I haven't learned the thing that you're talking about. It sounds like, but there should be a way that I can figure this out. Just making this integral work for me. Okay, so this is a surface integral. The g vector, is that just the acceleration due to gravity? Or is that something weird? I kind of forget. They probably defined g somewhere early on, right? Maybe not. Oh no, G is the gravitational field. Oh my god. So it's pointing the same direction as dA. If you integrate, and so G is the thing we actually want to find. If you integrate, they're pointing the same direction. So with this integral, I think we just end up having G times the surface area of a sphere. Yes! Okay. 4 pi r squared G. I think this is good. We're getting our linear scaling. Uh, minus 4/3 pi G rho R. We want to get rid of rho, though, do we not? Can we get rid of rho? Yeah, we can. Because rho is this. It's a constant. Oh, funny enough, that's going to cancel the 4/3 pi. GM R over R cubed. Yeah, that feels good. For R less than R. Okay, and so we for the other case, let's just steal the book's answer. Minus GM over R. And theoretically, if small r equals big R, these should match, and they don't. That's a problem. You go into the building and up one flight of stairs. Are you now on the first floor or the second floor? See, now that is something for all the measurements and things that Americans do weirdly, that is something we do right. You are on the second floor. You were already on the first floor when you first entered the building, hence it being the first floor. Having the ground floor and then the first floor makes no sense. My second G is phi. Oh my god. Well, you're on the first one. I did right, phi. Wait, we were supposed to get the potential? Oh my god, I got G, I didn't get phi. If you have G, you presumably integrate to get phi? Yeah, it should be like a negative line integral, I think. But in this case, the line, or it wouldn't be, you would just consider a straight line. So, I'm really weak on like, I think you undo the gradient on each side with the line integral. But that's a weird thing in Calc 3 where you have different types of integrals to undo different types of derivatives. Like you'd use a volume integral to undo that divergence. Same, Fembox. We can definitely see that this G goes from R squared to just R, though. So that's definitely the result of an integral in R. And that's the bit where you normalize it to vanish at infinity. And so would our phi of R... Do you actually need a negative? You should need... let's just do the integral first. We'll slap the negative on later. From infinity... Oh, if we do it like this, I think we're okay. I think we're building the negative sign in there. Maybe. I don't know. No. Yes? G is basically a force. Phi is basically work. You would integrate that force over a distance to get the work. My bounds aren't right though. Here's the thing. This formula is only valid up to capital R. That's the integral that I think we actually need. But we probably need to add... Do we need to do that? I think we need to do the integral from infinity to R for G from the outside. I feel like we need to do that. Tension decrease to minimum, system is stable. Yeah, I'm just getting confused on like the bounds of the integral and how that interacts with the sign. I might need the negative in front still. I just feel like I have a bunch of negatives already here. If I'm off by a sign, we'll figure it out at the end, I think. We do need another negative, don't we? Or, I don't know. My capital R's look like K's. Does the potentials wait, so the maybe I was misremembering. The field inside a charged sphere, the electric field inside a charged sphere, that's the thing that increases linearly with R? And the potential increases with R squared? Was I getting it wrong this entire time? It does? Okay. Okay, here's the question. Yeah, right. Definitely once we're outside, it should go down with 1 over R. Inside, it just is weird for it to go with R squared. Okay, so it is 2 pieces. You do just get 2 different terms. That makes me feel a lot better. My signs are all sorts of wrong, I think. But it is going to scale with the square. I was expecting the complete wrong result here, because I was getting field mixed up with potential. Actually, my signs, I guess, are okay. I do have the negatives there. So is what I have actually okay then? I feel like I've done something slightly wrong. But what's my final answer looking like if I get a common? Yeah, same $10. These coefficients don't really match up. I get the negative sign in the right spot. The coefficients might not be supposed to match up. I feel like they should, but they might not be supposed to be. Spherical shell instead of sphere. collapse past a given radius, coherent with the R linear factor of the potential, because the frontier of the sphere is drawn inside, even harder when it's far from the center. But we're finding that it's R squared, right? Not R? The R linear factor is for the field, not the potential. That's where my confusion has been stemming from. What is group theory? It's the study of groups. And groups are how do you describe a group? It's a set of something with an operation. And the operation has to meet, or the operation on that set has to meet certain properties. Like it has to be associative, it has to have an identity, and everything has to have an inverse. Given those things, you can make you can figure out a bunch of properties and stuff. Argument is the same. Okay. So, let's check the endpoints now. Or the border point. Hanging out with a girl today, she said she liked being called pretty. Now I think about it, perhaps an invitation for me to call her pretty. Yeah, I think so. Hey, Bruno. My group theory is pretty abysmal, Walter. Like, what kind of properties? Dom, the dating coach? Yeah. I might pivot into dating coaching. Okay, here. So Bruno's in the Twitch chat. It's like that chat up there is the Twitch chat. Walter, you're in the YouTube chat. I stream to Twitch and YouTube at the same time. So you need to have a binary operation on a set. So a binary operation could be like addition. You could deal only with integers and addition. And addition is your binary operation. And then once you've defined the set of numbers or things you want and the operation between them, you check your definition of a group, and that's the associative, identity, and inverses. And there's that hidden fourth thing you have to check for being closed, right, Jasu, for the binary operation. Once something has met the definition of a group, elementary properties of groups, that's what you want. You can say there is only one identity. If BA equals CA, then B equals C. And this stuff like this seems really basic, but it is very foundational to the building blocks of math. Gromov theorem? I assume that's not elementary, but maybe it is. Usually you don't assume that things commute. You don't assume that AB equals BA. But that is true for inverses, and you can show that. We can talk about like subgroups also. coordinate geometry is fucked. I don't know. Probably just look for an outside source. I don't really know though. But yeah, that's my crappy explanation of some properties of groups, I guess. What if we plug big R into this thing? Does it work? It might kind of work. Oh, I think it works. This is just, oh no, it's positive GM over R. It nearly works though. I just needed to reverse my signs apparently. I think so back when I set up these integrals, I probably did need to slap negative signs in front of them. So let's do that now. Just slap the negative signs on there. Okay, and now I think that works. I'm going to check the answer key. Definition group of nearly says so you have to work with them. That's fair, Matthew. Like you probably you do need to start talking about more like cyclic groups and stuff like that to get to the probably more interesting stuff. Number 4. Yep. I should just called it mu. I don't know why I used rho. Probably because I'm used to E and M. They use Poissons? Bruh. The Laplacian of phi. They're getting the spherical Laplacian here. What? They make it a differential equation? Wait. Yeah, this is for finding the potential. What's the Laplacian in spherical? Where is it? Curvilinear coordinates, I think? And they just care about that term because it doesn't depend on theta or phi. Now, why did they say 1 over dr? That doesn't look like a derivative with respect to r to me. I want to work out how they got from here to here. It's a common way? Huh. They don't write out the actual equation? GM over R... Wait, so this should be R squared... GM small r squared over 2 big R cubed. That's what I have. B is minus 3GM over 2R, which is what I have. Okay, so I did it. I got to the right result in a completely different way. I want to learn their way. Limited power sense requires computing Laplacian. Yeah, fair. Sorry, this might be the last thing that I do for the day here. But I do want to get from here to here. So I assume we multiply the r squared over and integrate each side with respect to r. What are my bounds? Do I care about bounds? No. We're going to do indefinite, I think. This is bad, isn't it? No, maybe it's okay. I can't tell if it's good or bad. It seems kind of good, kind of bad. Like I'm integrating an R again here. Now, which does not diverge at r equals 0. There is presumably some justification for chopping that off. Why can we chop that off? In general group theory you hate, adding same way to classify a group of order 168? Oh no. Sparkle 0 goes to infinity. Right, I see that, but we just chop it off? It just feels so cheatsy. As long as I can justify chopping it off, though, I've gotten the right form for AR squared plus B. Like, we're still deleting a lot of these coefficients that we found, but we can do that. Oh, is it one of those things where both of these solve the differential equation independently, but for this context, we only want one of the solutions? That's probably it. I'm going to check that, and if that turns out to be true, then I'm satisfied. So here I'm going to take B equal to 1 over R, I guess. So d phi dr is minus 1 over r squared. What should this be equal to? I guess 4 pi g mu over that. Either way, it's going to 0 though, right? And that's the issue. Because as soon as we get here, the r's cancel. And we're going to get a 0. So if I do this with the... Well, I just do AR squared plus B. What happens in this scenario? R squared, okay, d phi dr, 2AR. That's r cubed, 6AR squared. 6A is equal to 4 pi g mu. Okay, fair enough. I guess that's why. I think 1 over r does solve the differential equation, but we throw it out for physical reasons. Raspberry VNM here, computations. Yeah. Okay. That might be it for me for the day though, guys. I think I gotta call it. It's a very fun day though. See, I'm gonna have the YouTube stream off here. So Lou and anyone who's here on YouTube, thanks for being here. On Twitch, we'll look for a raid. But yeah, I'll see you YouTube.